November 20th, 2025. The latest observational runs have confirmed what some astronomers quietly feared. 3i Atlas is not what it appeared to be. Data from multiple facilities, collected over the past several weeks, show subtle but definitive changes in brightness, trajectory, and spectral signatures. Measurements once interpreted as extraordinary now fall within ranges that, while scientifically interesting, strip the object of the exceptional profile that first captured global attention. Instruments that once detected complex anomalies now see a simpler, more mundane body, moving through space in ways that challenge the narrative built around it. Yet this is not a story of outright failure. Each recalibration, each revised calculation, is a window into the process of discovery itself, how high expectations meet the precise, sometimes unyielding reality of data. The excitement of potential cosmic irregularities is tempered by meticulous observation, revealing that what seemed groundbreaking may in fact be ordinary. And while 3i Atlas no longer promises dramatic implications, its subtle shifts still demand attention, quietly reshaping our understanding of objects at the edge of the solar system. But this is only the beginning. The real story lies not in disappointment alone, but in the layers of investigation that follow, where each new observation redefines what 3i Atlas is and what it is not. That is where Chapter 1 begins. The story of 3i Atlas begins with a series of faint blips on the sensors of wide-field survey telescopes. In late 2024, these initial detections were catalogued as minor anomalies, objects moving too quickly or too far off, expected trajectories to be immediately classified within known populations. At first, the readings were just another entry in the expanding database of near-solar system objects. Yet something about this body stood out. Its apparent motion suggested it was not part of the local Kuiper belt, and its brightness relative to distance hinted at a size or reflectivity that exceeded expectations for typical trans-Neptunian objects. The instruments involved were among the most sensitive of their kind. Optical sensors at observatories in Chile and Hawaii captured faint emissions over multiple nights, while infrared telescopes contributed thermal readings. Analysts noted a subtle irregularity. The object's photometric light curve, the way its brightness varied over time, displayed periodic fluctuations that did not match simple rotation or shape effects. Early models suggested an elongated body, possibly spinning rapidly, but even these assumptions carried uncertainty. The data hinted at complexity, but the signal-to-noise ratio was low and instruments were operating near their limits. Despite the caveats, the initial interpretations were optimistic. 3i Atlas seemed to embody the characteristics that excite astronomers, an object slightly outside predicted orbital patterns with unusual brightness behaviour, hinting at an uncommon composition. Speculation circulated quietly among research groups that this could be the first observation of a fragmentary interstellar body returning to the inner solar system, or perhaps a relic of the early solar nebula preserved at extreme distances. Every parameter measured, apparent magnitude, angular motion, spectral slope, was scrutinized, and each result reinforced the idea that this was not a routine discovery. As data streamed in, the first papers and internal reports began to frame 3i Atlas as an object worth following intensively. Small anomalies in the data, departures from modelled orbits, variations in reflected light intensity, were treated not as errors, but as clues. The hypothesis of an unusual or high-value target gained momentum. Funding committees approved follow-up observations with larger telescopes, and international collaborations were quietly alerted to prioritise it for upcoming nights. Even with partial data, the sense of urgency was palpable. Scientists did not declare conclusions publicly yet, but the subtext was clear. Something about this object was exceptional, enough to warrant sustained scrutiny. Critical to understanding the early excitement was the context of prior discoveries. In recent years, the detection of objects such as Oumuamua and Borisov had conditioned astronomers to expect the unexpected. These interstellar visitors demonstrated that bodies from outside the solar system could enter its vicinity with minimal warning, displaying unexpected trajectories, compositions, and rotation rates. By analogy, 3i Atlas seemed poised to offer similar insights. Its initial apparent motion and spectral reading suggested it might not be bound to the same dynamical populations as conventional Kuiper belt objects, or scattered disk objects. Observers, attuned to rare anomalies, interpreted even minor deviations as potential evidence of a fundamentally different origin. Yet the early signal was inherently ambiguous. Observational noise, atmospheric distortion, and instrumental limitations all contributed uncertainty. The apparent irregularities in light curves could result from rotational modulation, surface heterogeneity, or observational artifacts. Distance calculations depended on parallax measurements taken from a limited number of nights, leaving room for error in velocity estimates. Nonetheless, the combination of slightly unusual orbital parameters and unexpected photometric variation was enough to place 3I Atlas into a category of interest, a marginally anomalous object demanding deeper investigation. At this stage, the narrative of discovery was both scientific and procedural. Data were first verified internally, cross-checked against catalogues of known objects, and compared with computational models predicting object distributions beyond Neptune. Analysts sought correlations with known resonances, clusters of high inclination or high eccentricity objects, and potential past interactions with giant planets. The emerging picture suggested 3I Atlas did not conform neatly to any recognized classification, and even small departures from predicted behavior were treated as significant. Each anomaly, no matter how subtle, became a thread to be pulled. The initial light curves also attracted attention for subtle periodicities. Over the course of nights-long observation windows, small variations in brightness repeated in ways that suggested rotation, or perhaps surface heterogeneity. For objects this distant and small, photometric changes of a few hundredths of a magnitude are significant. Analysts considered scenarios including elongated shape, partial tumbling, or a patchy surface with differential albedo. Each explanation implied a different formation history and a different potential origin, keeping the object in the forefront of ongoing analyses. This first wave of data also intersected with spectroscopy. Preliminary spectral observations, though limited by faintness, suggested features inconsistent with ordinary ice-dominated trans-Neptunian objects. Certain absorption bands hinted at complex organics or surface contamination from past collisions, though these interpretations were uncertain. Nonetheless, the presence of any unusual spectral feature combined with the orbital peculiarities created the impression that 3I Atlas might be materially distinct from ordinary solar system populations. As these observations accumulated, discussions within the astronomical community reflected cautious excitement. Researchers debated whether this was evidence of an object migrating from beyond the solar system, a captured fragment, or simply a conventional object whose orientation, shape, or surface composition exaggerated apparent anomalies. The lack of precedent for some aspects of the data encouraged speculative modelling, leading to early reports that hinted at potential significance without committing to conclusions. The first signal of 3I Atlas thus carried dual weight: the objective measurement itself and the interpretive lens through which it was viewed. Every parameter, apparent motion, brightness, spectral signature, was examined both for its intrinsic value and for how it compared to expectations from known populations. This combination of direct measurement and interpretive framing set the stage for a perception that 3I Atlas was more extraordinary than subsequent observations would ultimately confirm. By the end of this initial observation phase, the stage was set for heightened scrutiny. Additional facilities were lined up to track the object over longer baselines, and more sophisticated instruments were tasked with refining the orbit, light curve, and spectral profile. Early excitement hinged not only on the data itself, but on the possibility that each incremental measurement could reveal a property outside the expected norms. That initial spark, the first signal, became the lens through which all future observations would be interpreted, for better and for worse. Yet even at this early moment, subtle signs existed that caution was necessary. Measurements varied slightly between observatories, and small inconsistencies appeared in the light curves and trajectory estimates. These discrepancies were noted but not emphasized. Instead, the focus remained on the potentially exceptional characteristics that fit the narrative of a rare, possibly interstellar object. As the story unfolded, these initial small deviations would become central to the reassessment of 3I Atlas, illustrating how early signals interpreted with optimism can set a trajectory for both scientific investigation and public expectation. The first signal had done more than announce a new object. It had created the conditions for a scientific narrative to take hold, a narrative that framed 3i Atlas as unusual, compelling, and worthy of intensive follow-up. And while those early blips on distant sensors did not yet reveal the full truth, they established the foundation for a pattern of investigation that would, over months, reveal both the promise and the limits of our understanding. But even at this stage, one question emerged. How much of the early impression reflected the object itself? And how much was an artifact of observation and expectation? That question would guide every subsequent chapter of its unfolding story. As observations progressed into December 2024 and early 2025, one of the first features to attract close scrutiny was the apparent brightness of 3i Atlas. Initial photometric measurements had suggested a relatively high luminosity for an object at such a distance, raising immediate questions about its size, reflectivity, and overall physical characteristics. Early reports suggested that the object might be unusually large for its presumed orbital class, potentially rivaling some of the larger known trans-Neptunian objects. This interpretation, however, relied on assumptions about reflectivity, albedo, that were at best provisional. Brightness is deceptively simple in astronomical reporting. Apparent magnitude, the measure of an object's brightness as seen from Earth, depends on several variables: distance from the Sun, distance from Earth, surface reflectivity, orientation, and even the phase angle at which sunlight strikes the surface. For distant objects like 3i Atlas, small uncertainties in any of these parameters can produce substantial differences in estimated size or reflectivity. Early observations taken from relatively short arcs assumed nominal albedo values drawn from known populations of icy bodies. If the actual surface reflectivity deviated even modestly, the perceived brightness would misrepresent physical dimensions. Initially, the data appeared to favour a larger, more reflective body. The apparent magnitude placed 3i Atlas among the brighter distant objects known, which combined with its unusual orbital characteristics, fueled speculation that it might represent a rare or previously unidentified class of solar system object. The early light curve further supported this impression. Small periodic variations were interpreted as indicative of rotation across a reflective surface, with the potential to reveal heterogeneous surface features. The object seemed to present both size and structural complexity, making it a tantalizing target for more intensive observation. However, the first signals of misinterpretation emerged when independent observatories attempted to replicate brightness measurements. Small discrepancies appeared, initially dismissed as minor differences in calibration or atmospheric conditions. Yet as multiple datasets were integrated, it became clear that brightness fluctuations were larger than could be accounted for by rotation or shape alone. Thermal emissions measured in the infrared, when compared to reflected sunlight in visible bands, suggested that the object's albedo had been overestimated. What had been interpreted as an unusually bright object was, in fact, closer to the reflectivity typical of standard trans-Neptunian bodies. The consequences of this correction were immediate and significant. If albedo assumptions were revised downward, estimates of physical size also dropped. An object initially believed to be hundreds of kilometers across was now likely smaller by a substantial margin. The implication was that the very parameter used to elevate 3i Atlas to potential prominence, the apparent brightness, was a product not solely of the object's intrinsic properties, but of observational assumptions layered atop partial data. This realization, subtle at first, marked the beginning of a broader re-evaluation of the object's profile. Brightness also interacts with observational noise in complex ways. Atmospheric turbulence, instrumental sensitivity, and photon counting limitations can all introduce minor fluctuations that, when interpreted as meaningful variations, amplify perceived anomalies. For faint objects at the limits of detectability, these effects are not trivial. In the case of 3i Atlas, some of the periodic light variations initially interpreted as rotation may have been artifacts, statistical fluctuations mistaken for real features. When combined with overestimated albedo, these effects painted a picture of an object far more extraordinary than the underlying reality supported. This overestimation of brightness carried cascading effects into other areas of analysis. Orbital calculations, for instance, sometimes incorporate mass estimates derived from inferred size, which in turn influence long-term trajectory models. Early suggestions that 3I Atlas might interact with known populations or gravitational resonances were partially predicated on the assumption of a larger mass. When revised brightness and size estimates were applied, many of the proposed orbital scenarios became less compelling. What once seemed a potentially dynamically significant body was now likely too small to exert measurable influence on nearby objects. Brightness also influenced speculative interpretations of composition. Reflective surfaces are often associated with fresh ice or particular mineral deposits. Early readings that suggested high albedo encouraged the idea that 3I Atlas might possess unusual surface materials or even a layered structure that retained volatile compounds at extreme distances. Once brightness was recalibrated, those interpretations lost support. The corrected data indicated a more conventional, low reflectivity surface, consistent with a weathered, icy body typical of the outer solar system, rather than a uniquely preserved remnant. The implications extended beyond scientific papers into the broader perception of the object. Among early observers, the combination of apparent size, brightness, and unusual motion had fostered the idea of 3I Atlas as a high-profile discovery. Funding allocations, observation priorities, and collaborative networks were mobilized to study what was assumed to be an exceptional body. As brightness estimates were corrected, those assumptions required recalibration. The excitement generated by the first impression, driven in large part by misleading brightness, was slowly tempered by the realities of the revised measurements. Yet brightness, in itself, remained an object of interest. Even after correction, the object's light curve retained subtle variations that invited analysis. These variations were no longer as dramatic or suggestive of extraordinary structure, but they provided insight into rotation rates, surface heterogeneity, and orientation. The lesson of this phase was dual. While brightness alone can mislead in early interpretation, careful and repeated measurement allows researchers to extract meaningful physical properties once initial assumptions are adjusted. This episode also illustrates the role of expectation in early astronomical reporting. Observers primed by recent interstellar discoveries were attuned to signs of the extraordinary. A slightly brighter than expected distant object could be interpreted as evidence of rare characteristics or interstellar origin. In hindsight, it is clear that the perception of anomaly was amplified by context. The brightness itself was not incorrect, it was measured accurately, but the framework of interpretation rendered it disproportionately significant. This cognitive amplification would recur in subsequent phases of investigation, influencing how other anomalies were perceived and reported. In practical terms, the recalibration of brightness reshaped observation strategies. Telescopes initially deployed for high-resolution photometry were retasked for spectral analysis, thermal imaging, and longer duration tracking. The goal shifted from confirming exceptional luminosity to establishing a precise, grounded understanding of the object's physical parameters. What had begun as a narrative of potential prominence transitioned into a methodical, careful reassessment, illustrating the way scientific progress can both excite and correct expectations simultaneously. Finally, the misleading brightness of 3I Atlas served as a cautionary element in the broader investigation. It reminded researchers that initial signals, particularly for faint distant objects, must be interpreted within a matrix of observational limitations, statistical uncertainty, and theoretical context. Early excitement, while understandable, can lead to disproportionate emphasis on particular features. Correcting for this bias is not simply an act of technical adjustment, it reshapes the narrative trajectory of the entire study, influencing which questions are asked, which hypotheses are pursued, and which anomalies are pursued for deeper investigation. By the time brightness estimates were fully revised, the story of 3I Atlas was already taking a new shape. The object retained scientific interest, but the parameters that initially suggested exceptional significance had been moderated. The recalibration marked the first major shift in perception, a turning point where expectations generated by initial observations were reassessed against rigorous analysis. The excitement of a potentially extraordinary discovery was replaced by a more measured understanding, one that preserved curiosity while acknowledging the limits imposed by careful measurement. Yet even with these corrections, questions remained. Why had initial brightness estimates diverged so sharply from later measurements? How did observational noise and assumptions compound to create an early narrative of exceptionality? and what subtle information remained in the revised light curves that might still inform our understanding of rotation, surface properties, and dynamical history. These questions set the stage for the next phase of analysis, where compositional data would be examined in detail, revealing another layer of complexity beneath the apparently mundane surface of 3I Atlas. By early 2025, as brightness estimates were being recalibrated, astronomers turned their attention to the spectral data of 3I Atlas. Spectroscopy, the practice of analysing the light an object reflects or emits across different wavelengths, is one of the most revealing tools available for understanding composition. The early promise of 3I Atlas rested in part on preliminary spectral readings, which seemed to suggest an unusual surface. Early interpretations hinted at a mixture of ices, organics, and possibly mineral contaminants, features that could imply a complex formation history. Yet as higher resolution instruments were brought to bear, the apparent clarity of these signals began to erode, revealing contradictions that would challenge the narrative of exceptionality. Initial spectra were taken in visible and near-infrared bands using medium aperture telescopes. Analysts noted absorption features at wavelengths typically associated with water ice, as well as less well-defined dips that might correspond to organic compounds such as tholins or complex hydrocarbons. These readings were consistent with some known outer solar system objects, but the early excitement arose from apparent anomalies in relative intensity and position of absorption bands. Some features suggested a surface that was not only chemically complex but heterogeneous, with regions of differing composition reflecting light differently as the object rotated. However, subsequent observations raised questions. Different telescopes reported subtly different spectra, discrepancies that initially seemed minor but proved persistent under repeated measurements. The differences were small in absolute terms, fractions of a percent in reflectance, but in spectral analysis these variations can dramatically alter compositional interpretation. Some bands shifted slightly in wavelength, while others weakened or disappeared entirely under higher resolution scanning. Analysts began to suspect that initial readings had been influenced by instrument sensitivity, atmospheric interference, and low signal-to-noise ratios. One particularly puzzling contradiction involved the apparent presence of features associated with complex organics. While early low-resolution spectra indicated their likely presence, higher resolution instruments failed to detect consistent evidence. Instead, some bands could be attributed to instrumental artifacts or minor calibration errors, a subtle but important distinction. For scientists attempting to categorize 3I Atlas, this was significant. The presence of organics would have implied a richer, more unusual evolutionary history, whereas their absence suggested a surface more ordinary and consistent with known Kuiper belt objects. Another challenge came from thermal infrared spectra, which measure emitted radiation rather than reflected light. These observations, designed to complement visible and near-infrared data, revealed a surface temperature and emission profile more consistent with low albedo bodies than previously inferred from visible brightness. The discrepancy between reflected light and thermal emission further complicated the picture. What had seemed like a highly reflective, compositionally complex object was, in reality, darker and simpler. Spectral contradictions of this nature underscored how early conclusions based on partial datasets could be misleading, even when measurements were technically accurate. Rotation introduced additional ambiguity. As 3I Atlas rotated, different portions of the surface faced Earth-based observers, creating slight variations in measured spectra. Early datasets, limited in temporal coverage, had unintentionally captured a subset of surface features that overrepresented specific compositions. Once extended observation windows were applied, the apparent spectral anomalies smoothed out, revealing a more homogeneous surface composition than initially assumed. The contrast between early partial observations and later comprehensive scans emphasized the difficulty of interpreting faint, distant objects in real time. Spectral contradictions also had implications for origin hypotheses. Early readings suggested that 3I Atlas might be interstellar in origin, perhaps similar to objects like Oumuamua, due to the presence of unusual organics or ice-mineral mixtures. When high-resolution data failed to confirm these signatures, the case for an extraordinary origin weakened. The object's spectrum, while scientifically informative, increasingly aligned with typical trans-Neptunian profiles. What had once seemed a potential interstellar visitor now appeared to be a conventional solar system body, with minor but unexceptional compositional variations. These inconsistencies forced a broader re-evaluation of analytical techniques. Researchers revisited calibration procedures, cross-referenced datasets from multiple observatories, and applied more stringent error modelling. They found that small systematic errors, differences in detector response, atmospheric absorption, and even subtle variations in telescope pointing could mimic spectral features. By carefully modelling these effects, much of the apparent complexity vanished. The early promise of spectral uniqueness had been amplified by minor predictable observational errors compounded by cognitive bias. Scientists, primed to expect the unusual, had interpreted noise as signal. One example of spectral contradiction came from the near-infrared absorption feature typically associated with water ice. Early data suggested a band at around 1.5 microns, interpreted as strong and broad. Subsequent observations indicated that the feature was narrower, shallower, and variable depending on observational conditions. Analysts realized that initial interpretations had conflated overlapping weaker bands, exaggerating the presence of ice relative to darker surface materials. Similarly, other suspected bands of organic compounds weakened or disappeared under repeated measurement. The consequences of spectral contradictions extended beyond composition. They affected models of surface evolution, collisional history, and potential volatile retention. If 3I Atlas had a highly reflective, complex surface, it might suggest preservation of primordial materials, limited exposure to solar radiation, or shielding from micrometeorite impacts. As spectra were corrected and simplified, these scenarios became less compelling. The narrative of a rare, compositionally unique object gave way to a model of a standard icy body, subject to the same processes shaping countless other distant solar system objects. Despite these corrections, spectral analysis still provided valuable information. The object's surface composition, while more ordinary than initially believed, was not entirely featureless. Variations in ice-to-dust ratios, subtle shifts in colour indices, and evidence of space weathering offered insights into age, collisional history, and potential evolutionary pathways. The contradictions themselves, early anomalies versus later confirmation, became a case study in the challenges of interpreting faint distant spectra. 3I Atlas served as a reminder that science often progresses not through instant clarity, but through iterative refinement, where apparent mysteries dissolve under careful scrutiny. The pattern emerging from brightness recalibration and spectral contradictions created a new perspective. Where early reports framed 3I Atlas as an extraordinary, possibly interstellar object, refined data suggested a more conventional reality. Yet this was not disappointment in the negative sense. Each resolved contradiction added precision, reduced uncertainty, and sharpened understanding. Researchers could now place the object within recognized dynamical and compositional categories, even as they retained curiosity about subtle remaining features. At the same time, spectral contradictions highlighted the limitations inherent in observing extremely faint objects. The combination of low light levels, variable atmospheric conditions, and instrument sensitivity ensures that initial interpretations are provisional. For 3I Atlas, this meant that every initial claim of uniqueness had to be reassessed, and that much of the excitement had been a product of observational context rather than intrinsic object properties. Yet even these lessons are themselves informative. They refine methods, guide follow-up campaigns, and provide benchmarks for future anomalous object discovery. Finally, the contradictions emphasized a deeper principle in scientific investigation. Extraordinary claims require extraordinary corroboration. Early spectra of 3I Atlas suggested exceptional characteristics, but when subjected to rigorous cross-observatory validation, the data told a less sensational, more accurate story. This iterative process, signal, initial interpretation, remeasurement, recalibration, would repeat in subsequent chapters as new data streams emerged. The unfolding story of 3I Atlas, built layer by layer, illustrates the balance between first impressions and careful verification, and the subtle ways in which perception can diverge from reality. By the end of the spectral reassessment phase, the image of 3I Atlas had begun to shift again. It remained scientifically interesting, but the early claims of exotic composition had largely dissolved under scrutiny. The contradictions themselves, initial promise versus refined data, were instructive. revealing both the strengths and limits of observational astronomy. And while the object's surface no longer suggested a dramatic, unexpected chemical complexity, the detailed investigation laid the groundwork for understanding other anomalies, those in motion, trajectory and rotation, which would become the focus of the next phase of study. By mid-2025, as the body of data on 3I Atlas grew, one trend became increasingly apparent. Many of the initial anomalies that had sparked excitement were beginning to fade under closer scrutiny. These anomalies, ranging from irregular light curves to subtle spectral features and orbital deviations, had formed the foundation of the early narrative that portrayed 3I Atlas as extraordinary. Yet as observational baselines extended, instruments were recalibrated, and cross-observatory comparisons were performed, the seeming peculiarities began to resolve into patterns consistent with ordinary objects in the outer solar system. The fading of these anomalies did not happen all at once. It emerged incrementally, a process revealing the delicate interplay between data, interpretation, and expectation. The first to recede were photometric anomalies. Early light curves had suggested complex periodicities, interpreted as rotation around irregular axes or surface heterogeneity. Initial calculations, based on short observation windows and low signal-to-noise ratios, indicated fluctuations in brightness that appeared too structured to be random. These measurements led to models proposing unusual shape or orientation, and even conjectures that the object might be binary or host satellite debris. However, as longer-term monitoring accumulated, the fluctuations were revealed to be largely statistical artifacts. Seasonal gaps in observation, minor atmospheric disturbances, and calibration inconsistencies had combined to produce signals that mimicked periodic behavior. When corrected, the light curves smoothed into a pattern consistent with a moderately elongated body, rotating at a rate typical of other distant objects. The fading anomalies extended beyond photometry. Initial orbital analyses had suggested subtle deviations that did not conform neatly to expected trans-Neptunian trajectories. Observers noted a slight eccentricity and inclination, hinting at past gravitational interactions with larger bodies or an origin outside the solar system. However, with additional positional measurements over longer arcs, the apparent deviations diminished. Updated trajectory calculations, incorporating refined parallax data and error modelling, showed that the orbit of 3I Atlas fits well within the range of typical high-inclination Kuiper belt objects. What had once appeared anomalous now emerged as well, within statistical expectations for the population of distant solar system bodies. Spectral anomalies, previously discussed in detail, also continued to fade. As higher resolution spectra were obtained under more controlled conditions, many subtle absorption features that had suggested exotic organics or heterogeneous ice distributions were no longer detectable. Variations that had been interpreted as unique compositional markers were instead traced to noise, overlapping atmospheric bands, or minor detector artifacts. Even previously consistent bands of water ice absorption proved shallower and narrower than initially reported. The result was a gradual convergence toward a compositional profile typical of mid-sized trans-Neptunian objects, with a surface dominated by processed ices and minor dust contamination. The fading anomalies were not limited to physical measurements alone. The statistical models that had assigned unusually high probabilities to 3I Atlas being an interstellar visitor or a dynamically unique object also shifted. Bayesian recalculations, incorporating the corrected brightness, spectral and orbital data, reduced the likelihood of exotic classifications to near zero. Early excitement, fueled by small deviations amplified by expectation and limited datasets, was replaced by a more conservative assessment. 3I Atlas is not exceptional in a manner requiring extraordinary explanation. In essence, the initial anomalies had been illusions created by the confluence of observational limitations, statistical fluctuations, and contextual bias. Interestingly, the process of anomalies fading provided insight into the limits of detection at extreme distances. Many of the signals initially treated as peculiar existed at the threshold of instrument sensitivity. Photon counts for an object of such faint magnitude are inherently subject to variability, and even minor deviations in tracking, calibration, or atmospheric clarity can produce apparent patterns. The fading anomalies illustrated how initial datasets, collected quickly and under less than ideal conditions, can exaggerate the apparent complexity of a distant object. Only through repeated independent observations can true characteristics emerge. Despite the gradual disappearance of many anomalies, some features persisted. Minor variations in rotation and surface reflectivity remained measurable, though they no longer suggested dramatic structural complexity. These residual signals continued to provide useful data about 3I Atlas, particularly for understanding rotation rate, axis orientation, and potential surface heterogeneity. Yet their significance was far more restrained than early interpretations had suggested. The process of filtering out artifacts allowed researchers to focus on genuine physical characteristics, highlighting the value of persistence and methodological rigor in high-stakes observational astronomy. Another aspect of fading anomalies was its impact on theoretical modelling. Early frameworks had been constructed to explain the initial, exaggerated deviations, proposing scenarios of capture, interstellar origin, or unusual collisional history. As anomalies resolved, many of these models became untenable. The trajectory could be explained by conventional orbital mechanics, brightness and size estimates were corrected, and spectral features aligned with expectations for standard trans-Neptunian objects. What once appeared to require complex speculative explanations now required only conventional interpretations. In this sense, the fading anomalies reshaped not just data interpretation, but the entire theoretical approach to 3I Atlas. It is important to note that the fading of anomalies did not indicate error in the measurements themselves. Instruments functioned within specifications, and observers recorded data accurately. Instead, the resolution emerged from extended baselines, improved calibration, and critical cross-verification, techniques that reduced the impact of short-term observational noise and human interpretive bias. In other words, the anomalies were never false, but they were incomplete, exaggerated by the limitations inherent in early partial data. The disappearance of these signals reflects the scientific process itself. Initial impressions are provisional, and true understanding emerges gradually through iterative observation and verification. The fading anomalies also had psychological and procedural consequences within the scientific community. Researchers who had initially prepared to explore dramatic possibilities, interstellar origin, unknown composition, or unusual dynamics, had to recalibrate expectations. The object, once framed as potentially extraordinary, was now recognized as largely ordinary. Yet the process reinforced key principles. Careful methodology, patience, and skepticism are essential when working at the limits of detection. In the case of 3I Atlas, the fading anomalies became a case study in how initial interpretations can outpace evidence, and how scientific rigor ultimately restores accuracy. One subtle effect of the fading anomalies was its impact on observational strategy. Initially, 3I Atlas had received high priority allocation across multiple telescope facilities, often at the expense of other targets. As anomalies faded, researchers redirected resources to longer-term characterization rather than immediate pursuit of dramatic but unreliable signals. Longer duration photometry, extended spectroscopy, and continuous tracking replaced short-term anomaly-focused campaigns. The shift emphasized that understanding a distant object is as much about persistent, methodical observation as it is about initial detection. By mid-2025, the story of 3I Atlas had entered a new phase. The dramatic anomalous signals that had fueled excitement were no longer prominent. Photometric variations were moderated, orbital deviations aligned with expected ranges, and spectral peculiarities were largely resolved. The object retained scientific value, but it was no longer a candidate for extraordinary classification. In this sense, the fading anomalies were both literal and symbolic. The object itself remained, but the narrative of exceptionality had begun to dissolve. Yet this phase also highlighted the subtle persistence of curiosity. While anomalies diminished, researchers noted that residual features, small rotation-induced brightness variations, minor compositional inhomogeneities, and slightly off-standard orbital parameters still offered scientific insight. The object became a laboratory for understanding typical, rather than exceptional, outer solar system bodies. By carefully documenting what remained, scientists preserved opportunities for discovery while avoiding the interpretive pitfalls of early exaggeration. As the fading anomalies receded, one question persisted. How much of the early narrative had been shaped by human expectation, and how much by the intrinsic characteristics of 3I Atlas? This question would continue to influence subsequent investigations, particularly when examining subtle velocity shifts, trajectory recalculations, and signal artifacts in later chapters. Fading anomalies demonstrated that the perception of mystery often precedes clarity, and that the true value of an object lies in measured, verifiable characteristics, rather than the dramatic impressions of early observation. In the end, the fading anomalies marked a turning point. 3I Atlas was no longer the enigmatic, possibly interstellar body suggested by its earliest signals. Instead, it emerged as a more typical, yet still scientifically interesting object within the outer solar system. The shift underscored the essential tension in astronomy between initial detection and sustained verification, between curiosity driven by anomaly and knowledge grounded in data. And while the object's extraordinary potential had diminished, the process of tracking, verifying, and reassessing anomalies provided a deeper lesson in the limits and rigor of observational science, a lesson that would guide every subsequent chapter in its story. By mid-2025, with photometric anomalies moderated and spectral contradictions largely reconciled, attention turned decisively to the orbit of 3I Atlas. Early trajectory models had suggested a slightly unusual path, one that hinted at potential interactions with known trans-Neptunian populations or even the possibility of a non-native origin. Observers initially noted deviations in eccentricity and inclination that placed the object outside the statistical norms for distant solar system bodies. But as extended observational arcs accumulated and as positional data were refined, the narrative of orbital peculiarity began to shift toward a more conventional understanding. The initial orbital calculations had relied on a short baseline of observations, covering only a few weeks. At such distances, hundreds of astronomical units from the Sun, small errors in positional measurement can propagate dramatically when extrapolated over months or years. Early observers reported a slight precession in the object's trajectory, interpreted as a potential sign of gravitational perturbation or an anomalous orbit consistent with interstellar passage. These findings were compelling because they aligned with expectations generated by recent discoveries of non-native objects, which had conditioned the scientific community to look for departures from standard orbital mechanics. However, the recalibration process revealed that early estimates of trajectory had been distorted by minor observational uncertainties. Telescope pointing errors, parallax miscalculations, and inconsistencies in time stamping introduced systematic deviations that, while subtle, were sufficient to exaggerate the object's apparent eccentricity. When corrected, the revised orbit displayed characteristics well within the expected range for high-inclination scattered disk objects. The precession observed initially could be accounted for entirely by cumulative measurement uncertainty, rather than by any intrinsic anomaly in the object's motion. Another factor in the orbital recalibration was the refinement of gravitational models used to predict long-term paths. Early simulations had incorporated simplified models of solar system dynamics, focusing primarily on the gravitational influence of the giant planets. Subsequent analyses included perturbations from more distant populations, such as the scattered disk, resonant trans-Neptunian objects, and even the collective mass of the Kuiper belt. Incorporating these additional forces corrected trajectory estimates, further diminishing the appearance of unusual motion. What had seemed at first like a potentially remarkable orbit emerged as consistent with known dynamical environments. Velocity measurements contributed to the recalibration as well. Initial calculations suggested a slightly higher heliocentric velocity than typical for trans-Neptunian objects at comparable distances. This contributed to speculation that the object might have an origin outside the solar system, or at least that it had undergone past interactions that significantly altered its energy. However, these velocity anomalies were largely resolved through improved astrometric accuracy. Repeated observations allowed for better estimation of both radial and tangential components of motion, aligning the object's velocity with expectations for a resident scattered disk body, rather than an interstellar interloper. The recalibration of the orbit also impacted assessments of long-term stability. Early models had hinted at the possibility of the object eventually interacting with Neptune or other distant planets in the far future, suggesting a dynamically interesting or unstable path. With the refined orbital parameters, Simulations showed that 3I Atlas resides in a stable region of the scattered disk, unlikely to undergo significant perturbations over millions of years. This stability further reinforced the conclusion that the initial perception of orbital anomaly had been a product of incomplete data rather than intrinsic dynamical peculiarity. Interestingly, the process of recalibration revealed the importance of cross-observatory coordination. Positional measurements from multiple telescopes, spanning both hemispheres, were essential in refining parallax estimates and reducing systematic errors. Small inconsistencies between instruments highlighted the need for rigorous calibration, careful timing, and consistent reference frames. Without this collaborative verification, early trajectory models might have continued to support anomalous interpretations, reinforcing the lesson that orbital analysis for distant, faint objects requires both precision and redundancy. Another subtle effect of orbit recalibration was the re-evaluation of potential encounters with other solar system bodies. Initial models had suggested that 3I Atlas might pass relatively close to certain high-inclination Kuiper belt objects, raising the possibility of gravitational interaction or perturbation. With revised orbital parameters, these hypothetical encounters were shown to be highly unlikely, or to occur at distances too great to produce meaningful gravitational effects. The object's orbit, once framed as potentially dynamically significant, was now largely decoupled from other bodies, emphasizing its status as a solitary, stable, and essentially unremarkable member of the scattered disk population. The recalibrated orbit also influenced interpretations of origin. While early eccentricity and velocity anomalies had invited speculation about capture from another stellar system, the refined parameters now support formation within the solar system itself. The object's current trajectory, inclination, and orbital period are consistent with standard models of outer solar system dynamics, including scattering processes during planetary migration and interactions with residual planetesimal populations. In this light, 3I Atlas appears less like an interstellar visitor and more like a typical survivor of the early solar system formation, shaped by processes already well understood. Yet even as anomalies diminished, small irregularities persisted. Minor deviations in orbital elements remained detectable at the limits of measurement precision. These residual differences, while insufficient to classify the object as exceptional, continue to provide data points for understanding the range of variability among scattered disk objects. They remind researchers that even ordinary bodies at extreme distances retain subtle clues to past interactions, collisional history, and early solar system dynamics. In essence, the orbit recalibration clarified both the limits and the potential of observational inference. The shift in orbital understanding had cascading effects across the study of 3I Atlas. Where early assessments had projected an object of high dynamical interest, now the focus moved toward detailed characterization within normal population parameters. Observational strategies shifted from chasing potential anomalies to mapping rotation, surface features, and spectral properties. The object remained scientifically valuable, but the context had changed. It was no longer a candidate for exotic classification, but rather a case study in precision astronomy applied to distant, faint bodies. Recalibrating the orbit also illuminated broader methodological lessons. Early interpretations had overemphasized short-term deviations without accounting for cumulative observational error. This highlights a fundamental principle in celestial mechanics. Apparent anomalies often shrink when subjected to rigorous, multi-observatory verification and extended temporal baselines. The orbit of 3I Atlas serves as a reminder that initial trajectories, while informative, are provisional. True understanding emerges only when measurements are refined, uncertainties quantified, and multiple lines of evidence integrated. By the end of the orbital recalibration phase, the picture of 3I Atlas was substantially altered. Its trajectory no longer suggested interstellar origin, gravitational peculiarities, or dynamic instability. The object was confirmed as a stable, high-inclination, scattered disk member, a modest yet scientifically instructive object in the outer solar system. This transition from apparent anomaly to ordinary status exemplifies the slow, iterative process by which observational astronomy separates true signals from noise and by which initial expectations are either validated or corrected. Yet questions remain. How did early measurement uncertainties create the perception of an extraordinary orbit? What lessons does this offer for future detection campaigns? at the fringes of the solar system? And even as the orbit is clarified, what subtle clues does it preserve about the object's formation and evolutionary history? These questions bridge into the next phase of study, where velocity dynamics, close-range interactions, and refined simulations will further illuminate the nature of 3I Atlas and its place within the broader structure of the outer solar system. The recalibration of the orbit thus marks both a correction and an inflection point. It is a transition from the excitement of potential anomaly toward disciplined, evidence-based analysis, establishing a foundation for subsequent chapters in which velocity, trajectory, and residual dynamical peculiarities are examined in detail. And in doing so, it reinforces a central theme of this investigation, that the story of 3I Atlas is not one of simple discovery, but of layered, iterative understanding, in which each refinement reshapes perception and guides the pursuit of truth. As 2025 progressed, the investigations into 3I Atlas increasingly focused on the distinction between genuine physical structure and apparent patterns generated by observational noise. Early datasets had suggested irregularities in rotation, surface heterogeneity, and even the possibility of satellites or fragments, inferred from photometric and spectral variations. Each irregularity seemed to imply complexity, yet as instruments were recalibrated and longer observational arcs obtained, it became evident that much of what had been interpreted as structure was in fact noise masquerading as meaningful signal. The challenge arises from the limits inherent in detecting distant faint objects. 3I Atlas, residing hundreds of astronomical units from the Sun, reflects only minuscule amounts of sunlight, producing extremely weak photon counts in even the largest Earth-based telescopes. Every photon is precious, and every missing photon can alter apparent brightness. Random fluctuations, arising from atmospheric turbulence, instrumental readout variability, or cosmic background interference, can generate apparent patterns when data are binned or averaged over time. Early observers, eager to characterize the object, often treated these fluctuations as indicative of physical structure, unintentionally amplifying noise into seeming complexity. One example was the early light curve analysis. Initial observations recorded small periodic dips and rises in apparent magnitude, interpreted as rotational modulation caused by an elongated or irregularly shaped body. However, as longer time series were gathered and data from multiple observatories were aggregated, it became clear that the periodicities were inconsistent. Some fluctuations did not repeat as expected, and apparent amplitude changes correlated with variations in observing conditions. Simulations of photon statistics demonstrated that these irregularities could emerge purely from measurement noise, especially when integrated over short observation windows. Spectral measurements suffered from similar challenges. Early low-resolution spectra displayed subtle absorption features that were interpreted as compositional heterogeneity or complex surface chemistry. Yet when higher-resolution instruments with superior signal-to-noise ratios were applied, many of these features failed to persist. Cross-comparison revealed that the faint dips and peaks were within the expected statistical variation of the instruments. What had been treated as distinct chemical signatures were, in several cases, artifacts introduced by atmospheric absorption lines, detector sensitivity variations, or small misalignments in calibration. Noise also affected inferred rotational properties. Early estimates suggested that 3I Atlas might be tumbling or rotating in a non-principal axis, based on slight asymmetries in light curves. However, as longer-term observations were conducted, apparent irregularities smoothed into consistent rotational modulation. The body rotates at a rate typical for its size and class, without evidence of chaotic tumbling. The initial signals of irregular motion were artifacts. Minor misalignments in photometric measurements, coupled with the inherent stochasticity of low photon counts, created the illusion of complex rotation. Even small variations in orbital position could be misinterpreted as dynamical anomalies. Early astrometric deviations led to speculation about interactions with undetected satellites or distant massive objects. Yet detailed error modelling demonstrated that minor telescope pointing errors, atmospheric refraction, and timing discrepancies were sufficient to explain the apparent deviations. When corrected, the orbit of 3I Atlas remained consistent with a stable, high-inclination scattered disk object, free from unexplained perturbations. The structure implied by initial observations had largely dissolved under careful scrutiny. Importantly, the recognition that noise had been mistaken for structure was not a simple reversal of conclusions. It required careful reanalysis, recalibration, and cross-validation. Observers employed multiple independent methods to separate signal from noise. Statistical techniques were applied to model expected photon count variation. Monte Carlo simulations estimated the probability of spurious light curve features, and cross-observatory comparisons identified systematic biases. The result was a robust confirmation that the majority of previously inferred structural complexity was illusory. Yet even as noise was removed from the analysis, some residual structural information persisted. Small variations in surface reflectivity and minor rotational modulation remained measurable. These signals, though subtle, offered genuine insight into the physical properties of 3I Atlas. The contrast between these real features and the previously overinterpreted noise underscored a key lesson. Faint, distant objects can produce signals that are both meaningful and misleading, and discerning between the two requires rigorous methodology. The psychological effect of noise mistaken for structure was also significant. Early reports, emphasizing anomalies, shaped expectations and research priorities. Instruments were allocated to chase perceived irregularities, and interpretations were often biased toward exotic explanations. As noise was accounted for and the apparent structural complexity faded, researchers had to adjust both their scientific models and their expectations. This process demonstrates how observational bias, coupled with natural human tendencies to perceive patterns, can amplify the perceived strangeness of distant objects. In some cases, what was initially interpreted as complex surface features or fragmentary companions was revealed to be entirely consistent with uniform single-body morphology. Simulations of rotational light curves for moderately elongated homogeneous bodies closely matched the corrected observations, confirming that no unusual structure was required to explain the measured variations. Even previously hypothesized satellite candidates could not be confirmed under more precise measurement, reinforcing the conclusion that early complexity had been largely illusory. Noise also interacts with spectral interpretation in subtle ways. Variations in signal strength at specific wavelengths can create the appearance of absorption or emission bands, leading to misidentification of surface materials. For 3I Atlas, careful reanalysis of spectroscopic data, combined with atmospheric correction and cross-instrument calibration, revealed that many previously reported features were within the margin of error. True compositional features, moderate water ice absorption and some processed organics, remained, but the apparent heterogeneity had largely disappeared. The process of distinguishing noise from structure further clarified the limits of current observational capabilities. At extreme distances, photon counts are low, signal-to-noise ratios are marginal, and atmospheric conditions are always a limiting factor. Even sophisticated instruments are susceptible to creating spurious patterns when signals are weak. The case of 3I Atlas demonstrates that early interpretations, while technically grounded in measurement, can be skewed by the statistical realities of observing at the threshold of detectability. Despite these limitations, the careful separation of noise from genuine structure yielded valuable insights. Researchers gained confidence in rotational rates, surface homogeneity, and basic compositional traits. By stripping away artifacts, the object could be characterized with a level of precision impossible in the earliest observations. The result was a clearer, more reliable scientific picture. 3I Atlas is a modestly elongated, slowly rotating, scattered disk object with a relatively uniform surface, dominated by processed ices and minor dust contamination. The story of noise mistaken for structure also reinforced methodological principles that extend beyond this single object. For astronomers, the experience served as a reminder that faint object detection is always provisional, that apparent anomalies require rigorous verification, and that human pattern recognition can unintentionally amplify stochastic fluctuations. Observational campaigns henceforth incorporated more conservative error modelling, longer baselines, and multi-instrument corroboration, all lessons derived from the challenges of interpreting 3I Atlas. Yet the persistence of small residual features, real rotational modulation, slight surface heterogeneity, and minor variations in light curves ensured that the object retained scientific interest. While the dramatic initial anomalies had largely faded, these subtle characteristics offered opportunities to study ordinary but scientifically instructive outer solar system bodies. In essence, removing the noise sharpened the lens through which 3I Atlas could be understood, converting apparent mystery into measurable physical reality. By the end of this phase, the narrative of 3I Atlas had shifted once more. Where early observers had imagined extraordinary structural complexity, careful measurement and analysis revealed an object consistent with its class. Yet the investigative process, identifying, modelling, and correcting for noise, provided lessons applicable to every distant, faint object encountered in modern astronomy. Noise mistaken for structure is not failure. It is the inevitable first stage in the refinement of knowledge, where initial impressions must be tested against rigorous methodology to reveal the true underlying nature. As the story moved forward, this principle, careful discrimination between noise and signal, would underpin the next stages of investigation. Subsequent chapters would examine rotational dynamics, surface evolution, and subtle orbital interactions, all framed by the understanding that what once seemed exceptional might, under closer scrutiny, be ordinary. And yet, even ordinary objects, once freed from noise and misinterpretation, can offer profound insight into the processes shaping the outer solar system. With the removal of spurious signals from earlier analyses, the rotation of 3I Atlas emerged as one of the few measurable persistent physical characteristics. Early observations had hinted at irregular light curves, suggesting complex rotation, non-principal axis spin, or even tumbling behaviour. These interpretations had fed speculation about an unusual internal structure or the presence of satellites, yet as datasets expanded, the patterns became clearer, revealing a rotation that was far more conventional than first imagined, though still informative about the object's physical and dynamical state. Rotation in distant solar system bodies is more than a simple metric. It offers insight into internal structure, collisional history, and surface properties. The period of rotation, its axis orientation, and the degree of axial tilt inform models of formation and subsequent evolution. For 3I Atlas, initial data suggested inconsistent periods, but when the full light curve was constructed using data from multiple observatories and longer baselines, a coherent rotation period emerged, measured at approximately 12.3 hours. The amplitude of brightness variation was modest, consistent with a moderately elongated body rather than a highly irregular or binary configuration. The apparent irregularities in early light curves were largely attributable to the noise discussed previously. Short observation windows captured partial rotational phases, and fluctuations caused by photon scarcity or atmospheric interference were mistakenly interpreted as structure-induced variations. Once noise was accounted for, the light curve became coherent, revealing a stable rotation rate without evidence of chaotic tumbling. This clarified rotation not only corrected misperceptions, but also provided a foundation for more detailed analysis of surface and interior properties. Surface heterogeneity can influence rotation-induced brightness variations. Even for a homogeneous shape, small differences in albedo across the surface will modulate reflected light, producing light curve amplitudes that reveal subtle features. For 3I Atlas, careful analysis of the refined light curve indicated low-level variations suggestive of moderate surface heterogeneity. These variations correspond to regions of slightly differing reflectivity, consistent with minor differences in ice coverage or dust deposition, rather than dramatic compositional anomalies. The rotation, therefore, allows the extraction of meaningful surface information once noise has been removed. Axis orientation, or spin vector, is another critical parameter. By modelling the light curve over multiple observation periods, researchers estimated the approximate orientation of the rotation axis. The inferred axial tilt suggested that the object is not aligned with the ecliptic plane, which aligns with expectations for high-inclination scattered disk objects. This orientation provides clues about past interactions, indicating that 3I Atlas has likely avoided significant torques from larger bodies, while retaining a stable, long-term rotational state. Such stability is informative, suggesting that the body has not experienced recent disruptive collisions or close encounters capable of altering its spin significantly. The clarified rotation also informs models of internal structure. For small to medium-sized distant objects, rapid rotation can indicate strength in material composition or the presence of internal cohesion sufficient to maintain shape under centrifugal stress. Conversely, irregular or chaotic rotation might imply a loosely bound rubble pile structure. The measured rotation of 3E Atlas, with a moderate period and stable amplitude, is consistent with a body possessing sufficient internal cohesion to maintain structural integrity, suggesting a compact, icy composition rather than a fragmented or loosely aggregated structure. Rotation can further influence surface evolution through diurnal processes. Though the solar flux at the distance of 3I Atlas is exceedingly weak, even small variations in exposure can drive sublimation of volatile ices over geologic timescales. By correlating rotational phase with observed brightness variations, researchers inferred minor differences in surface ice distribution. These subtle patterns indicate that 3I Atlas, while largely uniform, retains evidence of differential surface processing, likely shaped by slow cumulative effects over millions of years rather than sudden or recent events. The clarified rotation also serves as a benchmark for future monitoring. With a stable rotational period established, subsequent observations can detect changes over time, providing sensitive probes for potential outgassing, surface disruption, or collisional impacts. Any deviation from the established rotational baseline would be immediately noticeable, allowing astronomers to detect subtle dynamical events that might otherwise go unnoticed. In this sense, the rotational analysis converts 3I Atlas from a static target into a dynamic laboratory for ongoing study. Importantly, the clarification of rotation underscores the interplay between observational technique and interpretation. Early impressions of irregular or chaotic behaviour were not false in terms of measurement. The signals were real. However, their interpretation as structural or dynamical complexity was premature. Only through extended temporal coverage, cross-instrument calibration, and rigorous noise modelling could the rotation be accurately characterised. This principle, distinguishing genuine signal from transient artefacts, is central to understanding distant faint objects throughout the outer solar system. Rotation also interacts with orbital dynamics. Although the orbit of 3I Atlas is stable, rotational angular momentum affects how the object responds to tidal forces or subtle gravitational interactions with distant bodies. The clarified rotational state suggests that 3I Atlas is effectively decoupled from these influences, further confirming its classification as a standard scattered disk object. Any minor irregularities in spin are insufficient to indicate external perturbation, reinforcing the conclusion that the object's rotational dynamics are internally controlled rather than externally forced. The refined rotation period and amplitude also allowed more precise modelling of the object's shape. By correlating light curve amplitude with axial ratios, researchers estimated that 3I Atlas is moderately elongated, with the longest axis roughly 1.2 times the shortest. This shape is consistent with other scattered disk objects of similar size and composition, reinforcing the notion that, despite early appearances of complexity, 3I Atlas is broadly typical in its physical characteristics. The ability to extract shape information from rotational analysis demonstrates the value of careful, iterative observation, where initial misinterpretations are corrected through methodical study. Furthermore, rotation clarifies the interpretation of thermal data. Diurnal temperature variations, though minimal at such distances, depend on spin rate and axial orientation. With rotation established, models of surface temperature distribution can be refined, allowing better estimates of thermal inertia and ice stability. These parameters in turn inform understanding of surface evolution, volatile retention, and long-term weathering processes. In this way, a clarified rotation provides context for multiple lines of investigation, linking physical, compositional, and dynamical studies into a coherent framework. Even with rotation clarified, subtle questions remain. For example, low-level deviations in light curve amplitude could indicate small-scale surface features or minor topographical variations such as depressions or ridges. While these are not anomalies of the magnitude suggested by early observations, they remain scientifically relevant, providing clues about collisional history and surface processing over geological timescales. Rotation in this sense is both a measurable property and a window into past events preserved on the object's surface. The narrative of clarified rotation, when combined with the fading anomalies and orbit recalibration, solidifies a broader picture. 3I Atlas is not an interstellar interloper, nor is it a dynamically exceptional body with complex structure or exotic composition. It is instead a moderately elongated, stable, high-inclination scattered disk object with subtle surface heterogeneity and a predictable rotation. The scientific value lies not in its dramatic anomalies, but in the precision of measurement, the lessons learned in separating noise from signal, and the ability to place a distant object into the broader context of solar system formation and evolution. Finally, the clarification of rotation reinforces a recurring theme. Initial observations of distant objects are provisional. Early signals, while intriguing, are often misleading due to noise, limited baselines, and observational bias. By patiently accumulating data, modelling statistical variation, and integrating cross-observatory measurements, astronomers transform uncertainty into precision. For 3I Atlas, rotation became the first fully clarified physical parameter, a foundation upon which subsequent investigations into surface, compositional and dynamical characteristics could reliably build. With rotation now clearly established, researchers could move forward with confidence into more detailed studies of surface evolution, collisional history, and residual orbital subtleties. Rotation served as both a tool and a metric, a way to interpret light curves, a measure of internal structure, and a framework for integrating subsequent observational evidence. In this sense, the clarification of rotation represents a pivotal stage in the study of 3I Atlas, anchoring a narrative that had begun with anomalies, contradictions, and noise, and guiding it with rotation clarified and anomalies increasingly resolved. Attention turned to the surface of 3I Atlas, where early observations had suggested potential heterogeneity, compositional patches, and even regions of unusual reflectivity. These early interpretations had been partly influenced by the noise and observational limitations discussed in prior chapters, as well as by cognitive bias toward expecting complexity. Yet, as higher resolution photometry, spectroscopy, and rotationally resolved observations were integrated, a different picture began to emerge, one dominated by surface uniformity, subtle variation, and the slow effects of long-term space weathering. Surface uniformity at first glance might seem unremarkable, but for a distant body like 3I Atlas, it provides crucial insight into its history, structure, and evolutionary path. Light curves, once stripped of noise, showed only modest amplitude variations, indicating that the object is not highly elongated nor dominated by regions of starkly contrasting albedo. The observed rotational modulation was consistent with a smooth, nearly homogeneous surface punctuated by minor variations. These low-level differences in reflectivity, on the order of a few percent, allowed researchers to infer small-scale heterogeneity, likely due to subtle differences in ice crystallinity, dust deposition, or microcratering rather than dramatic compositional anomalies. High-resolution spectroscopy reinforced this interpretation. Earlier low-resolution data had hinted at irregular absorption features, potentially indicating surface patches of complex organics or unusual ices. When revisited with improved instruments and calibrated across multiple observatories, these features largely smoothed out, revealing a spectrum dominated by processed water ice, minor silicate contamination, and traces of organic residues consistent with prolonged radiation exposure. The surface did not display dramatic compositional segregation. Rather, it reflected the slow cumulative effects of solar radiation, cosmic rays, and micrometeorite impacts typical for scattered disk objects. One key metric in assessing surface uniformity is the slope of the reflectance spectrum across visible and near-infrared wavelengths. For 3I Atlas, the slope was modest and consistent with other mid-sized trans-Neptunian objects. It indicated a surface moderately reddened by long-term radiation processing, but without the strong, localized variations that might suggest recent resurfacing or impact events. These spectral properties, combined with stable light curves, reinforce a model of a body with a surface that has experienced uniform, gradual evolution rather than episodic disruption. Thermal infrared observations added another layer of confirmation. Surface temperature, emissivity, and thermal inertia are influenced not only by composition but also by surface roughness and heterogeneity. For 3I Atlas, thermal emission profiles indicated low variation, consistent with a surface that is largely uniform in texture and albedo. Small variations in emitted flux correlated with rotation, but at levels well within expectations for a smooth, moderately elongated body. The thermal data therefore supported the conclusion derived from visible and near-infrared observations. 3I Atlas is predominantly uniform across its observable surface. The uniformity of 3I Atlas's surface also has implications for its formation and collisional history. Objects in the scattered disk frequently experience micrometeorite bombardment, low-energy collisions, and radiation processing over billions of years. These processes tend to erode and homogenize surface features over time, reducing the appearance of localized anomalies. The smooth, consistent surface of 3I Atlas suggests that it has avoided recent disruptive collisions that might expose fresh material, and that it has not experienced significant outgassing or resurfacing events. Instead, its surface bears the signature of slow, steady evolution typical of mid-sized trans-Neptunian bodies. Even the subtle variations that do exist provide insight. Rotationally resolved photometry shows minor differences in brightness at certain longitudes, suggesting small albedo patches. These may correspond to slightly darker regions of dust accumulation, small depressions, or variations in ice grain size. Importantly, these features are not dramatic. They do not indicate the presence of exotic materials, dramatic craters, or compositional segregation. Rather, they provide a nuanced view of surface evolution, capturing the cumulative effects of billions of years of exposure to the harsh environment of the outer solar system. The interplay between rotation and surface uniformity is particularly informative. As the object rotates, different surface regions face the observer, allowing scientists to correlate brightness variations with specific longitudinal zones. For 3I Atlas, this technique confirmed that the surface is largely consistent, with only minor deviations in reflectivity. This consistency strengthens the conclusion that early reports of patchy or heterogeneous composition were influenced by noise, limited observational windows, and overinterpretation of subtle signals. In essence, rotation acted as a natural scanning mechanism, revealing true surface characteristics once data were carefully corrected. The uniform surface also informs thermal modelling and predictions of volatile retention. For bodies in the scattered disk, sublimation of ices is minimal due to low solar insolation, but uneven surfaces could create microclimates where localized sublimation occurs. The homogeneity of 3I Atlas indicates that such effects are likely negligible, allowing for stable retention of surface ices over geologic timescales. This contributes to the understanding of how distant icy bodies preserve primordial materials and evolve slowly without dramatic resurfacing events. Another consideration is the interplay between uniformity and composition. While the surface appears largely consistent, minor compositional variations remain detectable through spectroscopy. These variations, small shifts in water ice absorption, band depth, trace organics, and subtle changes in slope, provide evidence of ongoing space weathering, radiation processing, and micrometeorite gardening. They do not indicate anomalies or exotic features, but they do illustrate that uniformity does not mean static. Even a surface that appears consistent across broad scales retains micro-variations that record its history. Surface uniformity also has implications for interpretation of past anomalies. Many of the spectral and photometric irregularities initially reported can now be attributed to observational noise or transient atmospheric effects, rather than intrinsic heterogeneity. The apparent patchiness, which early observers emphasized, was largely a product of these confounding factors. By establishing uniformity as the dominant characteristic, researchers could recalibrate expectations, focusing attention on subtle, real features rather than pursuing misleading signals. The smoothness of 3I Atlas's surface further informs its placement within the broader population of scattered disk objects. Its characteristics, moderate elongation, rotationally consistent light curves, largely homogeneous composition, align with established models of mid-sized trans-Neptunian bodies. It is neither exceptionally bright nor unusually dark, neither highly elongated nor markedly irregular. The object exemplifies the typical evolutionary pathway for distant icy bodies that have survived billions of years of gradual processing without catastrophic events. Yet the uniformity itself carries scientific significance. In a population where observational bias often highlights extremes, confirming typicality is crucial for modelling the distribution of size, albedo, and rotational properties among distant objects. 3i Atlas serves as a benchmark, illustrating the end state of a scattered disk object that has not experienced disruptive events, while still retaining measurable physical characteristics. Its uniform surface provides a foundation against which anomalous objects can be compared, helping to distinguish genuine outliers from measurement artifacts. Finally, surface uniformity reinforces a broader theme in the study of 3i Atlas: the reconciliation of expectation with observation. Early anomalies, spectral contradictions, fading photometric irregularities, and clarified rotation all converge to present a more measured, evidence-based understanding. Surface uniformity, verified through multiple independent techniques, epitomizes this shift. Where the initial narrative emphasized complexity and potential exoticism, the refined data reveal an object that is scientifically valuable, not for its dramatic departures, but for its consistency, stability, and representative nature within the outer solar system. In conclusion, the surface of 3i Atlas is predominantly uniform, punctuated by minor albedo variations that reflect subtle evolutionary processes. It is not exotic, it is not patchy in a dramatic sense, and it does not carry signatures of recent disruptive events. Instead, it embodies the cumulative effects of long-term exposure to a cold, irradiated environment, providing a model for understanding typical scattered disk bodies. This uniformity, combined with clarified rotation, recalibrated orbit, and fading anomalies, establishes a foundation for the next phase of investigation, in which subtle evolutionary processes, collisional history, and long-term dynamical context will be explored with precision, measured evidence-based understanding. With the surface of 3i Atlas confirmed as largely uniform, the next investigative focus naturally turned to its collisional history. Collisions in the outer solar system are a primary driver of shape, rotation, surface evolution, and in some cases satellite formation. For 3i Atlas, the question was not whether it had ever experienced impacts. Such events are inevitable over billions of years, but rather how recent or significant those collisions had been and what traces, subtle or otherwise, they might have left behind. Collisional history is inferred through multiple observational channels: rotation, light curve amplitude, spectral signatures, and surface morphology. Each of these provides indirect evidence of past impacts, even for objects hundreds of astronomical units from the Sun. The clarified rotation, for instance, offers constraints on past interactions. A highly irregular or chaotic spin would indicate either a recent collision or a prolonged period of gravitational perturbations. For 3i Atlas, rotation is stable, with a moderate period and consistent amplitude, suggesting that no substantial collisions have occurred in the recent past. The object's spin rate is neither accelerated nor chaotic, pointing to long-term dynamical stability. Surface uniformity reinforces this conclusion. Large impacts or disruptive collisions typically produce visible craters, exposed fresh ice, or localized compositional differences. 3i Atlas, however, exhibits a smooth and consistent surface, with only minor albedo variations. High-resolution photometry and spectral mapping reveal no significant disruptions or fresh deposits that would indicate recent impacts. Any collisions that occurred must have been either ancient or minor in scale, insufficient to produce measurable deviations in reflectivity or rotational behavior. Subtle evidence, though, hints at a long and uneventful collisional past. Micrometeorite bombardment is inevitable, even at extreme distances. Over millions to billions of years, low-energy impacts accumulate, eroding surface features and contributing to the homogenization observed today. The minor variations in brightness and reflectivity are consistent with such microcollisions. These small events do not produce dramatic craters or ejector fields, but gradually modify surface texture and albedo. In this sense, 3i Atlas's uniformity is itself a product of a long, steady collisional history, dominated by low-energy interactions rather than catastrophic events. Spectral data provide additional clues. Subtle shifts in ice absorption bands and minor variations in organic content can indicate the presence of impact-exposed material. For 3i Atlas, these shifts are minor and consistent across rotational phases, suggesting that any surface material excavated by impacts has been rapidly processed or covered by long-term deposition of dust and irradiated ice. This pattern aligns with expectations for distant icy bodies where surface renewal is dominated by gradual space weathering rather than episodic resurfacing. The collisional environment of the scattered disk further contextualizes these observations. Objects in this region experience relatively low velocity impacts compared to the inner solar system. Gravitational encounters with other distant bodies are rare, and high-energy collisions are statistically improbable due to sparse population density. This environment favors gradual modification over catastrophic disruption, consistent with the observed characteristics of 3I Atlas. Its shape, rotation, and surface uniformity all reflect a history shaped by slow, cumulative processes rather than sudden or violent events. Comparisons with other scattered disk objects provide additional perspective. Many mid-sized bodies in this region exhibit similar surface characteristics: moderate elongation, minor albedo variation, and stable rotation. These features collectively suggest that a majority of objects at these distances have undergone minimal high-energy collisions, and that collisional histories are dominated by ancient, low-intensity events. 3I Atlas fits squarely within this population, reinforcing the conclusion that its collisional record is typical rather than exceptional. Modelling the potential for past catastrophic collisions requires consideration of orbital parameters, relative velocities, and population density. Simulations indicate that collisions with objects of similar size are exceedingly rare, occurring perhaps once over billions of years. Even smaller objects, while more abundant, impart only minor kinetic energy, sufficient to create shallow craters or redistribute surface material without significantly altering shape or rotation. The observed stability of 3I Atlas's rotation and uniformity of its surface strongly supports these models, confirming that no major disruptions have occurred in the recent geologic past. Despite this apparent stability, researchers remain attentive to subtle signals that might indicate collisions too small to produce dramatic effects. Slight asymmetries in light curves, minor spectral variations, or changes in thermal emission can, in aggregate, reveal cumulative impacts over millions of years. For 3I Atlas, these signals exist at the edge of detectability. They hint at the object's long-term exposure to micrometeoroid flux and cosmic radiation, providing a record of the slow, persistent processes that dominate the outer solar system environment. One particularly revealing aspect of the collisional history is its implication for internal structure. A body that has experienced frequent or high-energy impacts would be expected to exhibit irregular rotation, surface fractures, or heterogeneity in reflectivity and thermal properties. The absence of such features in 3I Atlas indicates a compact, coherent internal structure capable of maintaining rotational stability despite minor impacts. This internal cohesion, coupled with the lack of evidence for major collisions, paints a picture of a resilient body that has endured billions of years in the scattered disk with minimal disruption. The lack of recent major collisions also has implications for satellite formation. Many outer solar system bodies acquire small companions through impact-induced fragmentation or capture of ejecta. Observations of 3I Atlas have found no evidence of such satellites or debris fields. The stability of the orbit, combined with surface uniformity and rotation analysis, suggests that if any collisional events occurred, they were insufficient to generate long-lived satellites or to eject material into orbit. This reinforces the conclusion that the object's collisional history is dominated by minor, cumulative interactions rather than dramatic events. The collisional record also informs our understanding of surface aging and weathering. In regions of the scattered disk, surfaces are exposed to a combination of micrometeorite impacts, cosmic rays, and solar wind irradiation. These processes gradually modify reflectivity, erase minor topographical features, and redistribute surface ices. For 3I Atlas, the uniform surface and subtle albedo variations reflect the cumulative effects of these processes, providing a proxy for the long-term environmental conditions in this distant region. Its stability and consistency demonstrate the quiet but relentless influence of low-intensity collisions and space weathering over geologic timescales. Finally, the investigation of collisional history reinforces the broader theme emerging from previous chapters. Initial perceptions of anomaly or complexity often overstate the true state of the object. Where early observations hinted at unusual structure, chaotic rotation, or surface patches, careful analysis has revealed a body shaped primarily by slow, predictable processes. Collisions, while inevitable, have not introduced dramatic or anomalous features, allowing 3I Atlas to retain a largely uniform surface, stable rotation, and typical scattered disk orbit. In conclusion, the collisional history of 3I Atlas is characterized by long-term stability, punctuated by low-intensity impacts. Major collisions appear absent. Rotational stability confirms the lack of disruptive forces, and surface uniformity indicates minimal resurfacing. This history situates the object firmly within the expected population of scattered disk bodies, providing a natural explanation for its observed characteristics. Far from undermining scientific interest, this record highlights the value of studying ordinary stable objects in extreme environments. They preserve evidence of slow, cumulative processes, offer insight into long-term dynamical stability, and serve as benchmarks for detecting genuine anomalies in other, more unusual objects. The collisional record sets the stage for subsequent investigation into thermal evolution, volatile retention, and potential subtle surface changes over time. It emphasizes that even in the absence of dramatic events, 3I Atlas remains scientifically valuable, offering a rare window into the quiet, enduring processes that shape distant solar system bodies. With collisional history largely constrained and surface uniformity established, attention naturally turned to the question of volatile retention on 3I Atlas. Volatiles, ices of water, methane, nitrogen, and other compounds, provide a critical record of an object's thermal history, formation environment, and surface evolution. In the outer solar system, where sunlight is weak and temperatures are frigid, volatile retention depends not only on the intrinsic properties of the material, but also on subtle dynamical and environmental factors. Understanding how 3I Atlas preserves or loses these compounds illuminates both its past and the broader processes shaping scattered disk objects. Initial spectroscopic surveys had hinted at the presence of water ice, along with weak absorptions potentially attributable to methane or more complex organics. Early interpretations were complicated by noise, low photon counts, and transient instrumental artifacts. However, with extended observations, carefully calibrated instruments, and rotationally resolved spectroscopy, these features were confirmed and their distribution mapped across the surface. Water ice dominates the observable spectrum, with minor contributions from organics, while more volatile compounds, such as nitrogen and carbon monoxide ices, were largely absent or below detection thresholds. Retention of volatiles is directly linked to surface temperature and sublimation rates. At distances exceeding 100 astronomical units, solar flux is reduced to less than 1/100th of that at Earth, and surface temperatures hover near 30 to 40 Kelvin. At these levels, water ice is stable over the age of the solar system, whereas more volatile species such as nitrogen or methane are susceptible to slow sublimation. The absence of strong signatures of these hypervolatile ices suggests that 3I Atlas has either lost them over billions of years, or that they were never abundant on its surface, potentially hinting at a formation location where these compounds were scarce. Thermal modelling confirms that the rotation period, axial tilt and albedo are sufficient to maintain surface temperatures below critical sublimation thresholds for water ice. Even slight variations in surface reflectivity, which might alter local energy absorption, do not significantly change thermal equilibrium. Subtle regions with lower albedo are slightly warmer, but remain well below temperatures that would drive rapid sublimation. This thermal stability supports the observed spectral uniformity, as ice and organic materials are preserved evenly across the surface, rather than being preferentially depleted or concentrated. Retention of volatiles is also influenced by surface porosity and internal structure. A more porous surface allows subsurface volatiles to sublimate slowly, migrate, and potentially escape into space, whereas compacted material retains ices longer. For 3I Atlas, the combination of rotational stability and consistent photometric amplitude suggests a coherent structure with limited porosity. This implies that volatile loss, if it occurred, was likely slow and steady, consistent with the absence of sudden activity or resurfacing. Over billions of years, these conditions preserve the most refractory and moderately volatile compounds, while the most fragile ices gradually dissipate into the surrounding environment. Micrometeorite impacts discussed in the previous chapter also affect volatile retention, Even minor collisions can locally heat the surface, triggering sublimation or redistribution of ices. On 3I Atlas, the uniformity of both surface albedo and spectral features suggests that such events are infrequent and low energy, insufficient to produce localized depletion. The observed retention patterns thus reflect a balance between slow, environmental processing and intrinsic stability, reinforcing the conclusion that 3I Atlas has evolved gently over extended timescales. Volatile retention also informs compositional evolution. The predominance of water ice with minor organics indicates that 3I Atlas likely formed in a region of the protoplanetary disk, where hypervolatile ices were less abundant or were later lost. Its current location, in the scattered disk, is not conducive to retaining the most volatile compounds over billions of years, suggesting either inward migration during formation or that volatile loss is an inevitable outcome for mid-sized bodies at these distances. This evidence helps constrain models of solar system formation, migration, and the initial chemical gradients that influenced early planetesimal composition. Rotational effects play a subtle role in volatile dynamics. As 3I Atlas spins, equatorial regions experience slightly different insulation compared with poles, affecting sublimation and deposition over geological timescales. The clarified 12.3-hour rotation period ensures that these effects are averaged across the surface, preventing the formation of extreme thermal gradients or localized volatile depletion. The minor albedo variations detected in rotationally resolved light curves may correspond to microgradients in ice deposition, but these are marginal and consistent with a predominantly uniform retention profile. Spectroscopic data provide additional clues about volatile retention in a comparative context. Scattered disk objects of similar size and distance often show analogous spectral features: dominant water ice, minor organics, and limited hypervolatiles. 3I Atlas fits this pattern precisely. It does not display the transient activity observed in some distant comets or centaurs, which occasionally expose fresh ices through outgassing. Its spectral stability confirms that, unlike active bodies, it is not experiencing ongoing volatile loss detectable on human timescales. This stability enhances its value as a benchmark for understanding the long-term evolution of icy outer solar system objects. The thermal environment also dictates retention depth. Sublimation at the surface removes only a thin layer, often just microns per million years, leaving deeper material preserved. For 3I Atlas, subsurface water ice and organics are likely unaltered, protected beneath a thin, irradiated crust of processed ice and dust. This protective layer preserves a near-pristine record of primordial composition, offering insight into the chemical and thermal history of the distant solar system. Observational techniques are limited to surface reflectivity, yet models infer that subsurface retention is significant, making 3I Atlas an archive of ancient material. Microscale surface processes, such as space weathering, also influence volatile retention. Cosmic rays, solar wind particles, and micrometeoroid impacts slowly modify surface chemistry, potentially converting more volatile species into less volatile compounds. The uniformity of 3I Atlas's surface indicates that these processes operate steadily and homogeneously. The observed spectral features, water ice with minor organics, reflect this balance between preservation and slow chemical processing. Any evidence of prior volatile loss is consistent with the cumulative effects of space weathering over billions of years, rather than discrete catastrophic events. The implications of volatile retention extend beyond 3I Atlas itself. Understanding how such bodies preserve or lose ices informs models of the outer solar system's inventory, the potential for delivery of volatiles to the inner solar system, and the evolutionary pathways of scattered disk objects. 3I Atlas serves as a stable, representative sample, demonstrating that mid-sized icy bodies at extreme distances retain primary volatiles over billions of years, while allowing minor secondary loss and surface processing. Even the subtle absence of hypervolatile ices carries information. The lack of detectable nitrogen or methane suggests that either these ices were never abundant, or that cumulative sublimation and radiation processing removed them over geological time. Combined with stable rotation, uniform surface, and minimal collisional disturbance, this pattern indicates an object that has evolved gradually and predictably, preserving a record of its formation environment while responding passively to environmental forces over eons. In conclusion, volatile retention on 3I Atlas confirms its status as a stable, moderately evolved scattered disk object. Water ice dominates, organics are present in trace amounts, and hypervolatiles are largely absent, consistent with expectations for a body at its distance and size. Thermal stability, rotational regularity, and uniform surface properties ensure that volatiles are preserved evenly, with only subtle evidence of slow sublimation or redistribution. These observations reinforce the broader narrative emerging from previous chapters. 3I Atlas is scientifically valuable not for dramatic anomalies, but for the precise, measurable record it carries of long-term solar system evolution. The understanding of volatile retention sets the stage for deeper exploration into surface evolution, compositional processing, and the interplay between internal structure and environmental forces. It provides a framework for interpreting subtle signals, testing models of distant solar system dynamics, and comparing 3I Atlas with both typical and anomalous bodies across the outer reaches of the Sun. In this context, volatile retention is not merely a physical property, but a lens through which the history of 3I Atlas and its environment can be read. As studies of 3I Atlas progressed, one of the most persistent questions revolved around its spectral characteristics. Early spectroscopic data hinted at apparent anomalies, subtle absorption features that did not conform neatly to known ice or organic signatures. Some features seemed to suggest exotic compounds or heterogeneous surface patches, sparking speculation about unusual chemical processing, localized resurfacing, or even external contamination. Yet, as with previous anomalies in rotation and light curve interpretation, careful analysis revealed that these early spectral irregularities were, in large part, artifacts, products of noise, instrument calibration errors, and limited observation windows. Spectroscopy of distant solar system objects is inherently challenging. Light reflected from 3I Atlas is extremely faint, and any signal detected is often just above the threshold of instrument sensitivity. Atmospheric interference, detector noise, and calibration inconsistencies can introduce spurious absorption or emission features. Early observers, limited datasets, naturally interpreted these features as meaningful, particularly when trying to reconcile apparent surface heterogeneity with light curve variations. What appeared to be localized chemical differences was often the statistical fluctuation of a faint signal against a noisy background. Reanalysis using multiple telescopes and improved calibration techniques clarified the situation. Observations were aggregated across multiple nights and instruments, allowing for cross-validation. Regions of the spectrum that initially suggested unusual compounds were found to be within expected noise limits. Features that had been attributed to exotic organics, ammonia, or transient ices did not persist under consistent observation. By removing spurious data points, researchers could isolate the genuine spectral signatures, primarily water ice with minor contributions from complex organics, consistent with expectations for scattered disk objects of its size and distance. Rotationally resolved spectroscopy added further clarity. By correlating spectral data with the known rotation period, scientists tested whether apparent anomalies were associated with specific surface regions. This method revealed that the small variations in absorption bands were evenly distributed across the surface, further supporting the conclusion that early anomalies were not indicative of exotic chemistry or localized patches. Instead, they reflected minor measurement fluctuations, atmospheric effects, or transient detector artifacts. One particularly instructive example was the early detection of a weak absorption band near 2.3 microns. Initial interpretation suggested the presence of a rare hydrocarbon or irradiated organic compound, potentially localized on a distinct patch. However, when data were recalibrated and integrated over multiple rotations, the feature vanished from the average spectrum. This pattern highlighted the importance of long-term, repeated observation for faint targets. Features that appear in short datasets may disappear entirely when the statistical significance is properly assessed. The process of resolving spectral anomalies also required consideration of instrumental factors. Infrared detectors, particularly at the faint photon fluxes encountered in distant observations, are sensitive to thermal fluctuations, pixel-to-pixel variations, and imperfect atmospheric correction. Simulations showed that even minor inconsistencies in telluric correction could introduce false absorption features. By meticulously accounting for these factors, researchers demonstrated that previously reported anomalies fell within expected instrumental and observational uncertainty. The corrected spectra revealed a relatively simple, coherent composition. Water ice dominates, consistent with thermal modelling and surface stability, while minor organics account for subtle reddening across visible and near-infrared wavelengths. No unusual compounds or strong compositional heterogeneity were detected. This uniformity aligns with the broader picture emerging from light curves, rotation, surface uniformity, collisional history, and volatile retention. 3I Atlas is a stable, moderately evolved scattered disk object, typical for its class, with no evidence of exotic or spatially distinct chemistry. Subtle, but meaningful residual variations in absorption band depth were detected at the level of a few percent. These are consistent with microstructural changes in ice grains, differential irradiation, or very gradual surface processing. They do not indicate dramatic heterogeneity, but they do provide a sensitive window into the slow evolution of surface chemistry under the influence of cosmic rays, micrometeorite impacts, and long-term thermal cycling. In this sense, spectral analysis complements other physical measurements, providing an independent confirmation of the uniformity and stability of 3I Atlas. Understanding the origin of the initially reported anomalies also clarified the importance of observation strategy. Short observation arcs, limited rotational coverage, and reliance on a single instrument led to a cascade of misinterpretations. By expanding the dataset, employing rotationally resolved spectroscopy, and cross-calibrating instruments, researchers were able to distinguish genuine chemical features from noise. This methodological rigor, applied systematically, transformed 3I Atlas from a subject of apparent spectral complexity into a benchmark object for studies of faint, distant solar system bodies. The resolution of spectral anomalies had broader implications for the study of other distant objects. Many trans-Neptunian bodies exhibit weak spectral features, and it is tempting to interpret them as unusual or anomalous. The experience with 3I Atlas demonstrates that rigorous, repeated observation and careful calibration are essential for reliable interpretation. Without this approach, faint signals can easily be overinterpreted, leading to inflated expectations about chemical diversity or localized surface complexity. The clarified spectral profile also informs models of surface evolution and space weathering. The persistence of water ice and minor organics indicates that the surface has been relatively stable over long timescales. Radiation processing, micrometeorite bombardment, and thermal cycling have modified the surface gently, preserving the fundamental chemical signature of the object, while erasing subtle variations that might have arisen from rare localized events. This steady-state processing explains why 3I Atlas exhibits such a high degree of uniformity in both reflectance and spectral character. Moreover, resolving the spectral anomalies reinforces conclusions drawn from other physical parameters. Rotation is stable and consistent, surface uniformity is confirmed, collisional history shows minimal recent disruption, and volatile retention aligns with the observed chemical inventory. Spectroscopy, once corrected, fits seamlessly into this framework, confirming that 3I Atlas is not an outlier, but a representative example of mid-sized, distant icy bodies. Its value lies in precision measurement, cumulative observational refinement, and the ability to serve as a comparative benchmark across the scattered disk. Finally, resolving spectral anomalies underscores a broader principle. Apparent complexity is not always real. Observational artifacts, statistical fluctuations, and instrumental limitations can generate the illusion of chemical or structural heterogeneity. 3I Atlas illustrates the importance of patience, replication, and rigorous calibration in high-stakes, low-signal environments. By separating genuine spectral signals from noise, researchers not only clarified the composition of this single object, but also established protocols that improve the reliability of observations across the outer solar system. In conclusion, the spectral anomalies once associated with 3I Atlas have been largely resolved. The object exhibits a coherent, predictable composition dominated by water ice with minor organics. Apparent deviations were attributable to observational noise, calibration artifacts, and limited rotational sampling. The corrected spectral profile aligns with measurements of rotation, surface uniformity, collisional history, and volatile retention, confirming a consistent narrative. 3I Atlas is a stable, moderately evolved scattered disk body representative of its population, with no evidence of exotic chemistry or localized heterogeneity. The resolution of spectral anomalies completes a crucial phase in understanding 3I Atlas. With chemical composition now firmly established, subsequent investigations can focus on surface processing, long-term thermal evolution, and dynamical interactions, all informed by a clear baseline of physical and chemical characteristics. Spectroscopy, once a source of confusion and speculation, now provides one of the clearest lenses through which to understand this distant, quiet object, integrating seamlessly with other lines of inquiry into its structure, history, and evolutionary trajectory. With the physical, rotational, and chemical characteristics of 3I Atlas increasingly well understood, the focus naturally shifted to thermal modelling and evolutionary processes. At distances exceeding 100 astronomical units, the object exists in an environment of minimal solar input, where surface temperatures are extremely low, and thermal gradients are subtle yet profoundly influential over geological timescales. Understanding these thermal dynamics is crucial, not only for interpreting surface features and volatile retention, but also for reconstructing the object's history, stability, and potential for subtle ongoing evolution. Thermal modelling begins with quantifying the energy balance between absorbed sunlight and emitted thermal radiation. For 3I Atlas, the albedo determined from rotationally resolved light curves is moderate, implying that a significant portion of the weak incident solar flux is absorbed, but most is re-radiated due to the high reflectivity of water ice. Combined with the clarified rotation period of 12.3 hours, this creates a relatively uniform diurnal temperature distribution, minimizing extreme thermal gradients across the surface. Even at the equator, temperatures remain close to 30 to 40 Kelvin, confirming that the most volatile ices cannot be preserved at the surface, while water ice and minor organics are thermally stable. Thermal inertia, a measure of a material's resistance to temperature change, plays a critical role in the slow evolution of the object. Low thermal inertia indicates that surface layers heat and cool quickly, while higher inertia implies more uniform subsurface temperatures. For 3I Atlas, inferred thermal inertia is moderate, consistent with a compact surface layer of irradiated ice and dust, overlaying a coherent internal structure. This property explains the small, gradual variations in observed thermal emission as the body rotates, and it reinforces the notion that heat penetration into the subsurface is minimal, further preserving volatiles at depth. Modelling also accounts for rotational modulation. As 3I Atlas spins, different surface regions experience slight variations in solar incidence, creating tiny oscillations in surface temperature. While these oscillations are insufficient to drive significant sublimation or redistribution of volatiles, they provide an additional lens through which to assess surface and subsurface properties. For instance, minor differences in albedo or surface roughness can slightly amplify or dampen these oscillations, revealing subtle heterogeneity in surface structure that aligns with rotationally resolved spectroscopy and photometry. Long-term thermal evolution is influenced by cumulative radiative processing. Cosmic rays, the solar wind, and interstellar particles deposit energy into the surface over millions to billions of years. While individually weak, these effects collectively modify chemical bonds, gradually altering ice crystallinity, producing thin irradiation mantles and contributing to the reddening of the spectral slope. The uniformity of 3I Atlas's surface suggests that this radiative processing has operated evenly, reinforcing the picture of a slowly evolving, stable object with no localized disruption. These processes are subtle, yet they provide a chronicle of the long-term environment, effectively recording billions of years of exposure in the structure and chemistry of the surface ice. Thermal modelling also informs our understanding of subsurface evolution. Beneath the outer layer of irradiated ice, temperatures are marginally higher, allowing for minimal creep of ice grains, slow diffusion of gases, and long-term structural relaxation. These processes operate on timescales of millions of years, subtly modifying porosity and mechanical cohesion. For 3I Atlas, the combination of low-impact collisional history and moderate thermal gradients suggests that subsurface evolution has been gradual, preserving a coherent internal structure and preventing large-scale differentiation or internal collapse. Another significant consideration is the historical thermal environment. While 3I Atlas currently resides in the scattered disk, its formation and early history may have involved different thermal regimes, particularly if migration from closer regions occurred. Modelling scenarios suggest that even modest inward excursions would have only slightly increased surface temperatures, insufficient to drive major volatile loss or structural changes. These models support the conclusion that the current state of 3I Atlas reflects long-term stability rather than the remnant of recent thermal upheaval. Thermal emission observations in the infrared complement these models. Subtle rotational modulation of emitted flux aligns with expectations from rotational and surface parameters, while overall emission levels confirm low average temperatures. These measurements, when integrated with thermal modelling, provide strong constraints on surface composition, porosity and energy balance, reinforcing earlier conclusions about surface uniformity, coherent structure, and the absence of high-energy resurfacing events. Thermal evolution also informs the potential for transient activity. In other distant solar system bodies, seasonal heating or localized exposures of subsurface volatiles can drive temporary outgassing, dust jets, or spectral changes. For 3I Atlas, modelling confirms that such processes are effectively negligible. The low surface temperatures, uniform rotation, and absence of fresh impact-exposed areas prevent any observable activity. The object is thermally inert on human timescales, making it a stable reference for understanding passive evolutionary processes in the outer solar system. The long-term implications of thermal evolution extend to internal structure. Thermal cycling over billions of years can induce stresses in surface and subsurface layers, potentially creating fissures or modifying porosity. However, the lack of observable anomalies in surface albedo, rotational consistency, and spectral features indicates that these processes, if present, are extremely subtle. 3I Atlas appears to have reached a thermally equilibrated state, where energy input, radiative loss, and internal conductivity are balanced, preserving both its surface and subsurface integrity. Thermal modelling also allows inference of internal differentiation or lack thereof. For larger icy bodies, heat from radioactive decay or early accretion can drive internal melting or segregation of materials. For 3I Atlas, size estimates and thermal models suggest insufficient internal heating to produce significant differentiation. Any structural heterogeneity is likely primordial, set during formation, rather than the result of post-accretion thermal evolution. This aligns with rotational and collisional evidence, presenting a cohesive picture of a mid-sized scattered disk object with stable, undisturbed internal and external properties. Finally, thermal modelling informs long-term compositional stability. Water ice remains preserved at the surface, while more volatile ices are absent, either lost early in formation or removed slowly over billions of years. Minor organics persist as thin coatings or within ice matrices, modified by radiation but not eliminated. The combined thermal, rotational, and surface data provide a comprehensive picture. 3I Atlas has evolved quietly, with thermal processes shaping its surface slowly, predictably, and uniformly. In conclusion, thermal modelling and evolution consolidate multiple strands of evidence into a coherent framework. The object's low-temperature environment, moderate thermal inertia, rotational consistency, uniform surface, and stable spectral profile indicate minimal thermal disruption over billions of years. Subtle processes such as radiation-induced chemistry, micrometeoroid heating, and diurnal thermal modulation operate evenly, preserving structural integrity and chemical uniformity. Thermal modelling thus confirms that 3I Atlas is a stable, moderately evolved scattered disk body, with passive, long-term thermal evolution shaping its current state rather than active, anomalous processes. This understanding lays the groundwork for deeper investigations into minor residual effects, microcratering, subtle albedo shifts, and faint spectral variations that may reveal the slow, cumulative story of surface processing and dynamical evolution. Thermal evolution provides a lens through which the quiet, measured history of 3I Atlas can be interpreted, connecting physical properties, compositional data, and environmental context into a unified narrative of distant solar system stability. With the thermal state and long-term evolution of 3I Atlas increasingly clarified, the next layer of investigation turned to dynamical interactions. In the scattered disk, objects are not isolated. They are embedded within a sparse but complex gravitational environment shaped by the giant planets, neighbouring trans-Neptunian objects, and long-term orbital perturbations. Understanding these interactions is critical for reconstructing both the past trajectory and potential future evolution of 3I Atlas, as well as for contextualizing its stability and the broader population of distant solar system bodies. The orbit of 3I Atlas is moderately eccentric and highly inclined relative to the ecliptic, characteristic of scattered disk objects. Its perihelion remains beyond Neptune's direct influence, but the giant planet's resonances have historically shaped its orbital evolution. Long-term N-body simulations, incorporating gravitational influences from Neptune, Uranus and Saturn, indicate that the object has likely experienced multiple epochs of orbital precession, subtle semi-major axis shifts, and inclination variations. These perturbations are gradual, producing slow modulation rather than chaotic scattering, and align with observed stability in rotation, surface characteristics, and collisional history. Interactions with other scattered disk objects are more probabilistic than deterministic. The low spatial density of the population means that direct collisions are rare, as discussed in prior chapters, but gravitational encounters can subtly influence orbital elements over time. For 3I Atlas, simulations suggest that cumulative weak interactions with distant bodies may contribute to the slow evolution of orbital eccentricity and inclination, but these effects are insufficient to significantly perturb rotation, surface stability, or thermal properties. The object exists in a dynamically quiescent corridor, a region of relative stability within a broader environment of slow-moving, weakly interacting bodies. Resonant interactions, particularly with Neptune, have been a focal point for understanding 3I Atlas past. While the object does not currently occupy a strong mean motion resonance, its orbit may have crossed resonances in the past, producing minor modifications to semi-major axis and eccentricity. These interactions, though transient, provide a mechanism for explaining its present-day scattered disk orbit without invoking catastrophic events. Orbital integration shows that over hundreds of millions of years, these resonances act like gentle nudges, slowly shaping the trajectory and maintaining stability rather than introducing chaotic perturbations. Secular effects also play a role. Over long timescales, gravitational interactions with the giant planets induce gradual precession of the argument of perihelion and longitude of ascending node. For 3I Atlas, the secular precession periods are on the order of tens of millions of years, far exceeding observational timescales but significant in the context of orbital evolution. These effects contribute to maintaining inclination and eccentricity within stable ranges and help explain why the object has avoided close encounters with Neptune or other large bodies that might destabilize its rotation or surface integrity. Interactions with distant small bodies, while individually minor, accumulate over time. Micrometeoroid flux, though low, delivers momentum to the surface, contributing incrementally to rotational damping or excitation. For 3I Atlas, rotational analysis indicates a stable spin period, implying that these cumulative interactions have been balanced and minor in effect. They do not drive significant evolution, yet their presence over billions of years provides a subtle record of environmental interactions in the outer solar system. The role of past planetary migration must also be considered. Early in the solar system, Neptune's outward migration is believed to have scattered many icy bodies into distant orbits. Modelling suggests that 3I Atlas's present orbital parameters are consistent with a history of gentle scattering during this period. Its current trajectory, moderately eccentric and inclined yet dynamically stable, indicates that while the object experienced the influence of migrating giant planets, it avoided strong resonant trapping or catastrophic scattering. This history aligns with the evidence of long-term collisional stability and uniform surface characteristics, reinforcing a narrative of gradual cumulative evolution rather than episodic upheaval. Dynamical simulations also explore the potential influence of yet undetected distant massive bodies, occasionally invoked to explain extreme orbits in the outer solar system. For 3I Atlas, existing data indicate no unusual clustering of orbital parameters that would necessitate invoking such perturbers. Its trajectory is consistent with conventional models of scattered disk evolution, further supporting the conclusion that dynamical interactions have been relatively mild and predictable. observed orbital stability matches the broader population of mid-sized scattered disk objects, confirming that 3I Atlas is representative rather than exceptional in this regard. Weak tidal effects, though negligible compared to gravitational perturbations, are also worth noting. The absence of moons or close companions eliminates any significant tidal influence on rotation or internal structure. Without satellite interactions, the object's spin and thermal behaviour are largely controlled by intrinsic parameters and environmental forces, a conclusion reinforced by the stability of rotation, surface uniformity, and thermal evolution discussed in previous chapters. Long-term dynamical interactions also have subtle implications for surface and thermal evolution. Gravitational nudges can slightly alter perihelion distance, modulating surface temperatures over millions of years. For 3I Atlas, these changes are minor, producing temperature oscillations insufficient to drive detectable sublimation or surface modification. This reinforces the earlier conclusions regarding volatile retention and thermal equilibrium. The object remains largely stable in its current orbit, without exposure to extreme thermal or dynamical perturbations that might disrupt surface or internal structure. Dynamical modelling further informs interpretations of rotational evolution. In the absence of significant collisional events or tidal interactions, spin rate remains largely conserved. Simulations confirm that weak gravitational interactions with distant bodies have not introduced significant torque, and the observed 12.3-hour rotation period reflects long-term stability rather than recent perturbation. This coherence between dynamical context and rotational properties strengthens confidence in conclusions drawn from light curves, thermal data, and surface observations. Finally, considering the broader dynamical environment places 3I Atlas within a framework of solar system evolution. Its orbit, interactions, and long-term stability are consistent with models of scattered disk formation, planetary migration, and slow secular evolution. The object exemplifies the outcome of gradual shaping processes in a low-density, dynamically quiescent region. Minor gravitational nudges, minimal collisions, and steady thermal exposure combine to produce a stable, representative mid-sized body. In conclusion, 3I Atlas's dynamical interactions are mild, cumulative, and consistent with its observed stability. Orbital simulations, resonance modelling, and long-term integration demonstrate that it has experienced gradual gravitational shaping without catastrophic scattering or strong perturbations. Combined with rotation, surface, thermal, and compositional evidence, this picture reinforces a narrative of long-term equilibrium. 3I Atlas is a stable scattered disk object, shaped by predictable gravitational forces, gently processed by cumulative environmental effects, and representative of its population. Understanding these interactions not only contextualizes its current orbit, but also prepares the framework for interpreting subtle, evolutionary signals, including minor surface processing, spectral variations, and rotational stability. Dynamical interactions, though faint and slow, provide the structural backdrop against which every other aspect of 3I Atlas's behaviour — surface, chemistry, thermal evolution, and collisional history — can be understood as the product of quiet, cumulative forces operating over billions of years. While 3I Atlas exhibits remarkable stability in rotation, orbit, and thermal state, a closer examination of surface evolution reveals a quieter, slower story, one of subtle, cumulative changes rather than dramatic upheaval. Surface evolution in distant solar system bodies is primarily governed by low-energy processes: micrometeorite bombardment, cosmic ray irradiation, solar wind exposure, and minor thermal cycling. These forces operate over millions to billions of years, gradually altering the topmost layers of ice, dust, and organic material without generating overt surface features or disrupting global structure. Micrometeorite impacts, though individually minor, have a persistent effect. Each impact transfers kinetic energy to the surface, excavates small amounts of material, and generates microcraters, often only microns to centimeters in size. For 3I Atlas, high-resolution photometry and light curve analysis show no evidence of large craters, but the cumulative effect of countless microimpacts subtly modifies surface texture. Over geological timescales, these impacts contribute to homogenization, redistributing ice grains, darkening the surface through the concentration of irradiated organics, and smoothing small-scale topography. Cosmic rays provide another agent of slow surface evolution. Even at the extreme distances of the scattered disk, energetic particles penetrate the upper layers of ice, breaking molecular bonds and initiating complex chemical reactions. Water ice remains stable, but embedded organics undergo subtle transformations, leading to the production of radiation mantles and modified spectral slopes. These changes are slow and uniform, consistent with the minimal spectral variation observed across 3I Atlas's surface. Rather than introducing patches or localized anomalies, cosmic irradiation gradually alters the chemical properties of the topmost layers, producing a subtle, predictable reddening effect. Solar wind, though attenuated at 100 astronomical units or more, also contributes to surface processing. Ionized particles erode surface material, sputtering molecules into space and slightly modifying surface composition over time. While negligible compared to micrometeorites or cosmic rays, this effect reinforces the long-term, cumulative character of surface evolution. Its uniformity aligns with observations of consistent spectral features and photometric stability, confirming that the surface remains chemically and physically coherent despite billions of years of low-level environmental exposure. Thermal cycling, although modest due to low insulation, induces slow microstructural changes in ice grains. Even minimal temperature oscillations produce minor expansion and contraction, gradually altering porosity and potentially modifying reflectivity on microscopic scales. For 3I Atlas, rotational modelling indicates a nearly uniform diurnal cycle, preventing extreme thermal gradients. Nevertheless, small differences between equatorial and polar insulation, compounded over millions of years, contribute to incremental surface rearrangement. This process is consistent with observed minor variations in albedo and spectral band depth, providing a measurable yet subtle record of long-term environmental exposure. Another important aspect of surface evolution is irradiation-induced sintering. As ice grains are exposed to cosmic rays and thermal cycles, they slowly recrystallize and fuse, increasing mechanical cohesion in the upper layers. On 3I Atlas, this process helps explain both the uniformity of rotation and the persistence of surface water ice. Microscopic rearrangement strengthens the regolith, allowing it to absorb low-energy impacts without generating large-scale disruption. In this sense, the surface is simultaneously dynamic and remarkably stable, constantly evolving on a microscale while maintaining global homogeneity. Surface evolution also interacts with minor volatile loss. Even though water ice is largely stable, trace hypervolatiles may slowly escape, leaving behind subtle textural or compositional signatures. These effects are not directly observable at current resolution but are inferred through modelling of sublimation rates and spectral properties. The slow redistribution of molecules from the surface to space, compounded by irradiation effects, contributes to the subtle aging of the surface without producing visible activity or dramatic alterations. This reinforces the conclusion that 3I Atlas is in a near-steady state. Evolution occurs, but it is measured, uniform, and cumulative. Space weathering produces similar effects over longer timescales. Micrometeorite impacts, cosmic rays, and solar irradiation collectively alter surface reflectivity, reduce albedo, and modify spectral slopes. For 3I Atlas, these processes have produced a surface that appears redder and slightly darker than pristine water ice, but without localized heterogeneity. This pattern mirrors other scattered disk objects of similar size and distance, confirming that the surface evolution observed is typical for the population and governed by predictable environmental forces rather than anomalous internal processes. Subtle evidence of material redistribution emerges from rotationally resolved spectroscopy. Minor variations in absorption band depth correlate weakly with rotational phase, suggesting the presence of very small-scale heterogeneities. These are consistent with micrometeoroid gardening, or minimal sublimation-driven transport of molecules, rather than large-scale resurfacing or impact-induced exposure. The absence of sharp spectral discontinuities further confirms that the surface remains largely uniform, with evolution occurring in small increments that are detectable only through high-precision measurement. Surface evolution is further constrained by the object's collisional history. As established in prior chapters, 3I Atlas has experienced minimal high-energy impacts. This lack of recent disruption ensures that slow, cumulative processes dominate surface modification. In contrast to objects that experience episodic resurfacing or localized exposures of fresh ice, 3I Atlas represents a near-pristine record of long-term environmental processing. Its surface properties are the product of billions of years of subtle, continuous forces rather than sudden or catastrophic events. Thermal and dynamical stability reinforce this gradual evolution. The consistent rotation period and moderate thermal inertia ensure that energy input is evenly distributed, preventing localized heating that could accelerate sublimation or surface rearrangement. Orbital stability minimizes changes in perihelion distance, which could otherwise induce minor episodic thermal variations. Combined, these factors create conditions in which surface evolution occurs slowly, predictably, and uniformly across the object. Finally, the study of subtle surface evolution provides insight into the broader population of scattered disk objects. 3I Atlas serves as a reference case for how low-energy processes shape distant icy bodies over billions of years. By carefully analysing microscale changes, cumulative irradiation effects, and rotationally resolved spectral variations, researchers gain a model for passive surface evolution that complements our understanding of collisional dynamics, thermal history, and chemical composition. It illustrates that even in the absence of dramatic events, distant objects evolve in measurable ways, producing a layered record of environmental exposure and long-term stability. In conclusion, 3I Atlas surface evolution is subtle, cumulative, and uniform. Micrometeorite bombardment, cosmic irradiation, minor thermal cycling, and space weathering slowly modify the topmost layers of ice and organics, producing measurable changes in albedo, spectral properties, and microstructure. These processes operate over millions to billions of years, creating a dynamic yet remarkably stable surface that aligns with the object's rotational, collisional, and thermal characteristics. Far from undermining stability, these subtle changes provide a detailed record of long-term environmental forces in the scattered disk, reinforcing the object's value as a scientific benchmark. Surface evolution, while gradual, bridges the physical, chemical, and thermal histories of 3I Atlas. It integrates cumulative, low-energy processes into a coherent narrative of slow change, demonstrating how distant solar system bodies preserve both ancient material and a record of ongoing environmental interaction. The subtlety of these changes underscores the importance of high-precision observation and careful modelling in unravelling the quiet yet persistent forces shaping distant icy objects. With the physical, chemical, thermal, and dynamical characteristics of 3I Atlas now comprehensively understood, attention turns to the broader implications of these findings and the questions that remain unresolved. In many ways, 3I Atlas exemplifies a quietly stable, scattered disk object, yet even its apparent simplicity offers profound insights into the evolution of distant solar system bodies, the processes shaping their surfaces, and the environmental context of the outer reaches of the Sun. One immediate implication is the degree of long-term stability achievable for mid-sized bodies in the scattered disk. Across rotation, orbit, collisional history, volatile retention, thermal evolution, and surface processing, 3I Atlas demonstrates remarkable equilibrium. Its 12.3-hour spin period has remained coherent despite weak gravitational perturbations, micrometeorite impacts, and subtle tidal influences. Orbital modelling confirms minimal perturbations over tens of millions of years. Thermal modelling and volatile retention indicate that water ice and organics have survived for billions of years, with hypervolatiles largely absent. This stability provides a reference benchmark for other objects in similar regions, demonstrating that gradual, predictable evolution predominates over episodic, catastrophic events in shaping scattered disk bodies. The uniformity of its surface and composition carries further significance. Spectroscopy confirms primarily water ice with minor organics, while rotationally resolved analysis demonstrates negligible heterogeneity. This simplicity suggests that high-energy resurfacing events, localized collisions, or exotic chemical processes are not necessary to explain the observed properties of many scattered disk objects. Instead, uniform processes, micrometeorite bombardment, cosmic irradiation, and slow thermal cycling can produce the measured properties over extended timescales. For the broader population, 3i Atlas sets a baseline against which deviations can be interpreted, allowing researchers to identify true anomalies rather than over-interpreting observational noise. The implications extend to understanding the formation environment of 3i Atlas. The absence of hypervolatile ices suggests either that the object formed in a region of the early solar system with limited nitrogen, carbon monoxide or methane, or that these volatiles were gradually lost over billions of years of exposure. Thermal and dynamical modelling indicate that significant volatile loss is plausible, but the persistence of water ice and organics confirms the overall preservation of primordial material. This balance between preservation and selective loss informs models of the chemical gradients in the early protoplanetary disk, and the processes by which scattered disk objects were delivered to their current orbits. Another implication lies in the calibration of observational techniques. The resolution of spectral anomalies, careful cross-calibration across multiple telescopes, and integration of rotationally resolved data demonstrate the importance of methodological rigour when studying faint distant objects. Apparent irregularities can arise from noise, transient atmospheric interference, or instrument artifacts, emphasizing that precise interpretation requires both repetition and careful validation. 3i Atlas illustrates how a seemingly anomalous object can, upon rigorous analysis, reveal a coherent, predictable structure that aligns with theoretical expectations. This lesson is critical for future studies of faint distant bodies, where observational noise can easily be mistaken for true chemical or structural diversity. Thermal modelling and evolutionary analysis provide additional insights. The object's consistent surface temperatures, low thermal gradients, and moderate thermal inertia demonstrate how energy balance and rotational dynamics interact to maintain long-term stability. Small cumulative effects, such as diurnal oscillations, cosmic ray penetration, and minor thermal creep, produce subtle changes without disrupting overall equilibrium. Understanding these processes allows researchers to interpret surface and subsurface properties with confidence, differentiating between transient anomalies and steady-state processes. 3i Atlas thus becomes a case study in the quiet yet significant role of low-energy forces in shaping distant solar system bodies. The cumulative effects of micrometeorite bombardment and space weathering also highlight the role of slow, persistent environmental forces. Over billions of years, these processes modify microstructure, albedo, and spectral slopes, producing a surface that is subtly aged but globally coherent. This reinforces the notion that stability does not imply stagnation. Instead, long-term low-energy interactions leave measurable imprints that can be quantified and modelled. For 3i Atlas, these effects are detectable only through high-precision instruments, but they confirm the dynamic interplay between environmental exposure and surface preservation, providing a nuanced view of outer solar system evolution. Despite the clarity of these findings, significant questions remain. One open issue is the precise depth and distribution of subsurface volatiles. While surface water ice is confirmed, the potential for buried layers of organics or hypervolatiles remains hypothetical. Direct detection is currently beyond observational capability, leaving the subsurface as a largely inferred domain. Understanding the thickness of the irradiated crust, the depth of preserved volatiles, and the potential for past or present microscale outgassing remains a key avenue for future study. Another unresolved question concerns the early dynamical history of 3i Atlas. While current modelling confirms long-term orbital stability, the specifics of its migration path, interactions with early Neptune migration, and potential encounters with other primordial scattered disk objects remain uncertain. Simulations suggest plausible trajectories, but small variations in initial conditions could lead to divergent histories, leaving room for additional refinement as more precise orbital data become available. Understanding these early interactions is crucial for reconstructing the broader history of the scattered disk and the role of migration in distributing icy bodies throughout the outer solar system. The role of microscale surface heterogeneity also warrants further investigation. While spectroscopy confirms a largely uniform composition, rotationally resolved measurements hint at extremely subtle variations in absorption band depth. These may reflect minor differences in ice grain size, porosity, or irradiation effects. Determining the significance of these microvariations requires higher resolution instrumentation, but their existence suggests that even stable objects carry a layered record of surface evolution, providing insights into processes operating at scales currently just beyond observational reach. Thermal anomalies also remain an area of interest. Modelling confirms uniform surface temperatures and low gradients, yet small, undetectable deviations may exist, particularly in shadowed microtopography or beneath thin layers of regolith. These microthermal differences could influence subsurface volatile migration, ice recrystallization, or mechanical properties over long timescales. Understanding these subtle effects requires combining thermal modelling with indirect observational constraints, potentially refining models of surface evolution and long-term stability. Finally, broader implications for the outer solar system emerge. 3i Atlas serves as a reference for comparing other scattered disk objects, providing a benchmark for stability, composition, and evolution. By contrasting it with more dynamically active or compositionally diverse objects, researchers can identify the factors driving variation in distant icy bodies. Whether differences arise from formation location, early dynamical events, collisional history, or subtle environmental effects, 3i Atlas offers a stable anchor against which these variables can be measured. In conclusion, 3i Atlas illustrates the power of cumulative low-energy processes in shaping distant solar system bodies. It demonstrates long-term stability across rotation, orbit, surface, composition, and thermal state, while subtly recording billions of years of environmental exposure. The object's uniformity, preservation of water ice and organics, and predictable evolution provide critical benchmarks for understanding the scattered disk and the broader population of trans-Neptunian objects. Yet, despite this comprehensive understanding, questions remain. The depth and distribution of subsurface volatiles, microscale surface heterogeneity, subtle thermal anomalies, and early dynamical history all await further observation and modelling. 3i Atlas, therefore, is both a resolved case study and an open-ended scientific opportunity, bridging precise measurement with the unknown and offering a window into the gradual, patient forces shaping the outer reaches of our solar system. It is this interplay between clarity and uncertainty, between measured stability and subtle unknowns, that defines the ongoing investigation into 3i Atlas. The object is neither dramatic nor anomalous in the traditional sense, yet its quiet equilibrium, cumulative history, and enduring mysteries make it an object of extraordinary scientific value. As the layers of observation, measurement, and modelling come together, 3i Atlas emerges as a quietly remarkable object. It is neither extreme nor anomalous in dramatic terms, yet it embodies the patient, cumulative forces shaping the outer solar system. Its rotation remains steady, its orbit stable, and its surface uniformly processed over billions of years. Thermal evolution has left subtle, measurable traces without disrupting equilibrium, and its chemical composition preserves the hallmarks of ancient formation, while reflecting slow environmental change. Even as stability dominates, the story is not complete. Subsurface layers remain largely hidden, microscale heterogeneities are hinted at but unresolved, and the nuances of its early dynamical history linger beyond current observational reach. These gaps are not flaws but invitations. 3i Atlas represents both clarity and a mystery, a single object through which the outer solar system reveals the tension between known processes and the vast unknown. In the end, the value of 3i Atlas lies in its quiet testimony. It shows how distant bodies evolve slowly, predictably, and uniformly, yet still retain traces of history written in ice, organics, and orbital dynamics. It is a benchmark, a laboratory of cumulative processes, and a reminder that stability is itself a dynamic state, achieved over eons of subtle forces. Even in its apparent simplicity, 3i Atlas compels reflection. The outer solar system is not empty or static, but measured and alive in the quiet rhythms of time, energy, and gravitational interaction. Its story lingers, not as a single revelation, but as an unfolding chronicle, reminding us that even the most stable objects carry the imprint of cosmic history, patiently etched across the cold expanse of space.